Good morning, good afternoon, good evening, wherever you are, ladies and gentlemen. Welcome to TechBeats Live. I'm your host, Kosseila, aka Cloud Dude. For those who don't know me, I'm the founder of Cloud3. I'm very passionate about LLM, especially the infrastructure layer. I usually host the TechBeats Unplugged podcast, but today is our very first live stream, and I couldn't be more excited. I hope you're here to learn, to ask some questions, and most importantly, have some fun with us because we have some good things waiting for you. And what we're here for today, we're here for a laid back but very insightful talk about what is LLM quantization, why it matters, how it works, and where it's all going. And I'm so excited to have not one, but actually two amazing guests with me today. I'm so lucky. So are you. Together, they represent two most impactful sides of the quantization space in LLMs. On one side, you have the consumer end, and on the other side, you have the enterprise one. And I think you're going to get the best out of how quantization will play out in the future on both worlds. As I said, we have on one side Eldar Intro, who brings the enterprise production perspective through this work, his work with vLLM at Red Hat AI. And on the other side, we have the legend Bartowski, the blacksmith of quantization, very famous in Twitter, in 𝐓𝐞𝐿, aka 𝐁𝐞𝐜, who's right at the heart of the GGUF scene and Llama.cpp, and also one of the most downloaded quantized models, GGUF models in 𝐓𝐞𝐿, if I'm not mistaken. So I can't wait to start. And without further ado, let's rock and roll. Okay, let me just welcome my guests. First, Eldar Intro, welcome. Happy to have you. And first question is, how you doing?
Thanks a lot for inviting me. Yeah, I'm doing pretty good. Yeah, excited for the talk
awesome.
today. Yeah.
Awesome, man. Colin, thank you for coming. Thank you for accepting the invitation, and welcome again. How you doing today?
Great. Yeah, looking forward to having a good chat here. And,
nice. Good. Great. Awesome. Just for the audience, Eldar is coming all the way from Austria, and Colin is coming from Ottawa, Ontario, in Canada. I'm from Ontario too, from Toronto. So this is kind of a transatlantic live stream, if we can say so, right? So we're ready to rock, ready to hit the ground. And what I wanted to start with, actually, for the audience to know you a bit more and break the ice, is to introduce yourself a little bit more. I'll be starting with Eldar. Tell us who you are and how did you get into the world of LLMs and quantization, hopefully before GPT was there, so before 2023. So can you just let us know a little bit more about your journey?
Yeah, definitely. So basically I started like with doing some research on computer vision for self-driving cars. This was before LLMs became a thing. And yeah, at the time, one of the main challenges was how do you actually put these at the time large neural networks inside the like a device inside the hardware that you have in the car. And that was about the time when I started like exploring quantization, pruning, and all these tricks. Yeah, I was really into quantization and pruning of computer vision models, and then ChatGPT happened, and yeah, we had to shift the entire focus to LLMs, which has been more or less the focus for the past few years now. Yeah, and yeah, I'm working like in a research team at Red Hat, most in the intersection of vLLM and the LLM compressor projects.
So sorry, you do have a PhD or?
No, actually, I don't have PhD. Yeah, I started a PhD, but then I joined Neural Magic, and yeah, I kind of took over a bit more the applied research path.
Got you. So they kidnapped you from school.
Yeah,
that's what happened.
Yeah, more or less, yes.
Nice. Okay, so you came from So you joined Neural Magic. Can you explain to people like what Neural Magic? I know they've been acquired by Red Hat, but just tell them like how the startup started.
Yeah, definitely. So the startup started at MIT with Professor 𝐁𝐞𝐴𝐻. So basically, the idea was at the time to run neural networks on CPUs. So at the time, that was the main target. So we developed an engine called DeepSparse, and that was our like main product for a while. And we've been able to get some really good like inference performance numbers on commodity CPUs, which are like more or less like very competitive with GPUs at the time. But yeah, then LLMs arrived and everything pushed a bit more towards the GPU side. These billion scale models made running on CPUs quite challenging. So yeah, we pivoted a bit towards the GPU side, and then we joined the vLLM project, and that was that became the main focus for the last few years. Yeah.
Crazy. And you're one of the main contributor to vLLM too, I guess, like with the
no, actually, I'm mostly on the LLM compressor side. So there is completely different.
I was talking about NeuroMagic in general.
Yeah,
NeuroMagic too.
I think NeuroMagic, at least the NeuroMagic team, which is now in the Red Hat, is I think at least one of the top 3 I think contributors to the vLLM at this point. Yeah, so they're pushing really hard into the open source, and yeah, with the like folks from UC Berkeley and other companies, they're trying kind of to push the boundaries of the kernels that we have these days. Yeah, and all of our quantization work relies on them writing really good kernels.
Exciting, man. Appreciate it. Oh, that's a cool intro. And you were here to explain to us the quantization in the enterprise / vLLM side of things, of course, today, right?
Yeah, that's right.
Can't wait. Okay, now should I call you Bartowski or Colin? That's
just call me.
Like I mean, for us.
I'm happy with either. I respond to both.
Really? Okay.
Yeah.
Could you introduce yourself and just tell us? I know you work at RC. That's how we call it. RC.
Yeah.
RC.ai. Could you tell us how did you find yourself here? Mingling between models and transformers.
Yeah, sure. So yeah, hi, I'm Colin. A couple years ago, I guess at this point, the main thing that kind of pushed me into the world of OpenAI, or OpenAIs, not OpenAI, was when this tool called 𝐓𝐞𝐿LLama v2 started becoming a thing. It was turbo derp over on GitHub, slightly lesser known model quantization scheme. But basically the idea was it was very state of the art. It was lots of targeted bit rates, but no one was really making it on release. So I wanted to use models with this. So I decided I would start making them on just like a little 3060 12 gigabyte that I had purchased off Kijiji or Craigslist for those outside of Canada.
Yeah.
And then it kind of grew from there. I bought a 3090. I started releasing more and more, and I switched over to GGUF, I think, after a few months, because it just like the workflow was easier to automate, and it wasn't. 𝐓𝐿LLama v2 takes a long time on consumer hardware. It's a slow process to make a full model, whereas I was able to push out GGUF pretty quickly. So all that kind of got me noticed by someone named Lucas, who works at RC. He picked me up. He started working with me mid last year. And then earlier this year, January, I got a full-time position over at RC and have been working there since and enjoying it.
Amazing. Awesome. And obviously, like you're very humble about it, but a lot of people that download the models, the GGUF ones, after the block only swear by the name of Bartowski. But I'm grateful for your work, because I've been using a lot of your models, Quantize models. But one question I wanted to ask you is, when you said you switched from again, remind me, the
𝐓𝐿LLama v2.
𝐓𝐿LLama, right? Mm-hmm. So the v2, when you moved from v2 to GGUF, can you tell us what time did you do it? Like which year and what period?
I think that was late 2023 was the main transition. It might have been mid 2024. I'm pretty sure it was at least very early 2024, very late 2023.
Okay. Yeah, because a lot of people started to discover GGUF like end of 2024. So
right.
Maybe me included, but I just wanted to put some carbon 14 right there. Just check your involvement in the scene, which is very awesome. Right. So now that we had the intro from both of you, there's like the first question, since the audience is pretty much eclectic, so I don't want to go to dark math. Really, this is like a chill, as I said, a laid back stream. Like, we're not here to just talk softmax or scaling factors only. This is not just for the people that have like AI leader in their LinkedIn profile or something like that. This is for literally anyone who wants to be dig into it or interested or curious. So the first question. Before we get to the question, I had a bet actually. You said Bartowski, and then there's a guy whose name is there's a character called Chuck Bartowski from a TV show from the late. That was my bet. Okay, I didn't for the record, I didn't ask Colin the question until today, until now, like like right now. So I want to know. Is Bartowski related to the character Chuck Bartowski from a super nice and cool and funny comedy TV show back in 2000s, or no? Or I'm like completely off?
No, that's 100% where it's from.
100%. Okay, cool. Cool.
Yeah,
that's super nice.
It was a very big influence in my growing up.
Got it. It was my influence too. So I don't blame you. Actually, one of the fans, especially the early seasons. I was a junior engineer, so when I heard Bartowski, I was like, I know Chuck Bartowski. Oh, okay. But most of you followers in Twitter probably don't know. But sorry to spoil everyone the original name. Okay, now let's go to the real question. I was about to look for a different phrasing for this question. So I explained quantization like I'm 5. Last time I wanted to say like explain quantization like I was your grandma. But then again, that could have been like a big challenge. But more or less, I want you guys to try to explain with your words what is LLM quantization to someone who's not into LLMs, who's maybe like just the aunt or the uncle or somebody who's not into IT, but he's using every day maybe quantized models, right? Especially through some of the new DeepSeek models and stuff like that. Some of them are quantized and they don't even know they're using them. How would you go with it? So I'll start with Colin. Can you give us like for layman's terms of like how would you tell someone who's not into it what it is?
Yeah, I mean, at the simplest form, which is obviously what we're going for, it's just taking what is a very large model and trying to shrink it down without losing too much of what makes it special, so that it can be run faster, easier on consumer hardware. Consumer hardware being really the main thing that drives the open world. Obviously, there's an enterprise side of things that I'm sure Eldar will touch on. But yeah, basically, it's like, how MP3s are, you still hear the song thoroughly, but it's significantly smaller than it was originally. And that's kind of the magic that is quantization of large language models. Great.
Eldar, any thoughts?
Yeah. I mean, that was a perfect explanation. I've just add that, it's like a process through which we are mapping either weights or activations of the models like to discrete buckets. So previously, when we have unquantized model, it can more or less take any possible value, but through the quantization, we try to map them into the discrete buckets. Which can be represented in the desired data type. But that's, I think the calling it probably like the really good explanation with a small add-on.
Got you. Also, like compression, we've been using compression for a long time for pictures, videos. I don't know, like maybe back in the days, being in college, or people used to download movies and there's a word called DVD rip, where you go from like full Blu-ray to like a decent quality, or the 16 or 600 and 700 megs instead of 2 gigs. Same thing with MP3 as well. Right, so that's like making something big and compress it into something smaller, lighter, but with a decent quality. That's what I would go for. Yeah, because back in the days, people used to listen to 20 songs in one CD. but thanks to the MP3 revolution, we have a bit more, and now we're going for even crazier number. Yeah, so I really hope people are, got a bit of a grasp of what quantization basically is. Just compression of a medium, and with at least like a maximum sort of fidelity in terms of accuracy. The second question is why it matters, right? So like why quantization matters, because so far we heard about Facebook buying, like the previous years, they used to buy 350K GPUs from H100 and then B200. And not only it's expensive, but it consumes a lot of energy. So like I would like to have your insight, guys, on why quantization matters in the world where I just want to remind everybody that according to Gartner, 80% of AI hardware will be dedicated to inference by 2028, right? So this is a lot of inference workload, and you better have either a lot of money or smaller models eventually. But yeah, so Eldar, I'll start with you. Why do you think quantization matters in this world of GPU greedy kind of consumption?
Yeah, I have two main use cases in mind. The first one is basically to optimize for latency. So if we are not satisfied with the latency that we get from the model, so we have to wait a bit more, and we would like to get the answer faster from a model. So quantization is one way to go there. Like you could just optimize the model so it starts generating the tokens faster. And the second one, yeah, of course, is like reducing the number of GPUs that we need to use to deploy a model. Like I think, like for example, the DeepSeek R1 or this K2 instruct model, which were like I think the most popular ones recently. Usually you would need two, for example, H100 servers just to deploy a model. Whereas if you do like 4-bit quantization or something of that kind, you can actually fit it inside a single server. So yeah, it just unlocks many more possibilities for consumers who don't have that many GPUs.
Great, excellent. Colin?
Yeah, obviously there's also the consumer side of things in edge compute, like where sometimes it's better to run a small model at full precision, but we've been finding more and more that running a slightly larger model at a quantization tends to be more performant, just because there's a higher density of information, and quantization is surprisingly lossless. Lossless is a strong. I meant to say you lose surprisingly little based on how much you compress. And that's similar to other compression techniques that exist. It's not like it's very particularly special in that way. But it is interesting to note that, yeah, you get a lot of the performance at a quarter of the size.
Interesting. And I think in terms of energy, that's that's a lot. The kind of there's an interesting metric that's called in data centers that's called the PUE. I don't know if you heard about it. It's called the power usage effectiveness, right? So basically that means that for example, if you have 1.2 PUE, that's basically means that for every 1.2 watts that you're using in your data center, you pull in 1 watts goes to the workload, to the inference, and then 0.2 watts are just wasted into cooling. All right. So when you have like, concentrated supercluster like this, depending on the kind of energy they're using, you may have, like the average is 1.2 for data centers, but it can go even higher depending on the type of energy. So you can have like 1.8 where you're spending maybe like sort of 0.8 gigawatts just on cooling. You're not even, you're just cooling those GPUs actually, right? When Sam Altman used to say, you're making the GPUs melt, maybe it's just not a metaphor. Maybe something else than metaphor. Right. So, and then the next one is training versus inference. What do you guys have in terms of thought around the importance of inference nowadays compared to training, or maybe the usage of quantization in inference and also in training? Where is the impact better? More significant? Obviously, I just said that 80% of the AI hardware will be used for inference by 2028, according to a report. But like, what is your perspective? I can start with Colin.
Sure. Yeah. I mean, obviously, I don't have any kind of insight into the training versus inference hardware, but we did see one interesting thing, which was DeepSeek. When they trained their model, they trained it at it's called FP8, which is different from what was typical of people to use, which was BF16. So the main thing to focus on there is the 8 versus 16. So it was half the size for actually training, which was unusual at the time. People usually tried to train with as much precision as possible because there's all these tiny, tiny little changes that happen as you train the model step by step. Inference obviously is kind of more so the golden standard for where quantization is used. Because it just, you don't need to necessarily run it at the same percent, like, especially going to FP8. It's basically indistinguishable from BF16, and you're already dropping half the size there. And what you can do with that half the size, you could also quantize the I won't get into it, but the KV cache. And so to Steven's point in the chat there, yes, sometimes it's about trying to run it faster on the same hardware. And one of the ways you can run it faster on the same hardware is by allowing the model to take up more space with its caching. And that way you can actually speed up concurrent requests. So maybe at full precision, you could only handle 2 requests at a time. But at half precision, you can now handle 4 requests at a time. And that actually doesn't add any extra latency. It just straight up doubles the performance as long as you have 4 requests coming in.
Excellent. Thank you. Eldar?
Yeah, so
any thought?
I mean, nothing more special to add on top of this. Like I think, like as Colin mentioned, DeepSeek was, I think, the first one which like managed to produce like very stable training with FP8 and get to like a very performant model. There is some work on getting this to even lower bit widths, like training in FP4, like in 4 and so on. But usually none of these academic papers have still shown that this scales well, like with larger models, because I'm not sure whether it doesn't work, or maybe it's just like because in the academic like environment, it's not that easy to train very large models. But there are papers for actually showing that we can do this even to 4-bit and push even more. But there is still this kind of huge question mark on whether we'll be able to scale that. But
yeah, it's like where's the trade-off? Like at a certain point, you're having to shove so much more data through for not that much more quality once you go to really low bit rate. So it's difficult there.
Yeah, that's very important. Like especially like because like as you go lower in bit width, usually we need more tokens to converge. Like as Colin just pointed out, and yeah, that it becomes like a really good question of like, does it actually make sense to push more if we have to put in more trillions and trillions of tokens, right?
So
whereas on the other hand, we have these like post-training quantization tricks, which we are both using in Llama.cpp community and vLLM, which can do a pretty decent job these days. And then it's just a matter of what makes more sense.
So there was a question here. Is there any good way to benchmark the actual response quality loss? I think you replied, Colin.
Yeah. Well, first of all, it is subjective. But yes, they're in a future slide we'll be talking about.
We'll talk about evals. Yes, definitely. So what I wanted to maybe review or go through again is it pretty much depends on the hardware. And the previous generations were trained on full precision because maybe they didn't have tensors that could support lower bits. Am I right?
That is part of it for sure. Like we do have more FP8 tensors now in modern chips. That's become more of a focus. And there was also like if you look at the specs, there's some of them where I can't speak to why this happens. The hardware does not make sense to me. But running at FP32 was like at a certain number of flops, And then for some reason running at FP16 was like double or like half the speed, despite the fact that it's half the size. It's just something about the way the architecture is set up that doesn't work well. So yeah, that is likely the case that we didn't have optimized hardware for this.
Right. I've seen the MI350 series from AMD recently in Keynote, and then they have FP4 as well in their core tensors available. So I guess the lower sort of bits support the hardware has, the more you can involve quantization even at the training or pre-training stage. Is that correct?
Yeah. So basically, yeah, like the number of like there's like for example, if you look at the H100, like BF16 has I think 2,000 teraflops. So there are like tensor cores for BF16 operations, and they're like I think 2,000 teraflops, something like this. And then as you go to Int8 and FP8, this doubles like to more or less 4K in flops, and that's basically what you can leverage. But then the problem is that if you go below that, then there is no hardware support. So you cannot get faster than that, and you just can do it just for the sake of having a smaller model at the end and leverage that during inference. But during training, that's the limit, at least with us. But now like Blackwell, and as you mentioned from AMD, it comes with FP4 tensor cores. So it's gonna be 2x on top of the FP8 in flops. So we'll be able kind of to push even more for this. But then
Nice,
the other question is stability of the trading and so on.
Exactly. But on the inference side, like there's not real limit because, we'll see later in the slides, we will even go for extreme quantization with like really, really super, super low bits for sure. The biggest misconception about quantization, since like you're working with it on a day-to-day basis, did you have anything to share about maybe some people, customers or like partners or peers that are working not from your field, but that are maybe consuming AI, where they may have some misconception about quantization?
Yeah, I can start with this one. Yeah, actually learned recently so RC published a blog post about quantization in particular for the purposes of running on CPUs, because there's been a little bit more push lately for high capacity CPUs, especially from Amazon with some ARM chips. I don't remember the names of them off the top of my head, but anyways, point is, yes, Graviton, thank you. Quantization, I think probably the biggest misconception is a combination of just not even knowing it's a thing, like not realizing that this is a concept that exists, and then even if they realize that it exists, the concept that we're still using this naive approach of just cut the bits in half, like take the 8, cut it here. All right, this is what we got now. Mm-hmm. Like we didn't care about but that's not what basically anyone's doing anymore, and hasn't been for a couple of years now. But yeah, instead there's quite a few algorithms that this 4 bits is not really 4 bits. It's 4 bits plus basically. Of
course. Eldar?
Yeah, one thing that actually I found quite interesting is the fact that Int4 models, for example, like weight-only quantized models, at least when running them on GPUs, there are cases when they are slower than the unquantized models. So we can even, I think I can maybe show some plots later on. But basically, once we increase the number of like requests that we are sending towards the model, so there is this distinction like between memory bandwidth bottlenecks and the compute bottlenecks. We can get into that later, but basically, once we cross this boundary and go from the memory bandwidth bottleneck to compute bottleneck, Int4 actually becomes slightly slower than an unquantized model. And that's something that people usually don't expect to see in practice, because there's always this kind of, if it's quantized, it's always faster. So that's something that we always have to take care about when we're talking about quantization and efficient inference.
Yeah. Actually, I watched your presentation. It's even for me, it's really hard. Sometimes I gotta watch it again to remember when is it memory bound, when is it compute bound, because it's so hard. You know what I mean? So it's like false positive and false negatives. A lot of people are confused of what is false positive, what is false negative. And in the compute bound and memory bound, sometimes I really have to go back and read the doc and realize which operation is compute bound, in which case, which scenario we're memory bound instead, for sure. So thanks. And also, a lot of people think that as soon as you quantize, that's what I notice, the quality is going down, like cheap down, which is not always true. Do you guys confirm?
Yeah. I mean, there's a point at which, yes, it does. And there are some diehards who say, give me BF16 or give me def. But there is definitely an amount of quantization that can be applied where it'll be indistinguishable.
Yeah. It's not, you're not going to write like a, Pulitzer article or I don't know, a novel that would have a price. Obviously, you won't use a quantized model for that.
Yeah,
for sure. But there's a lot of things you can do with quantized models, for sure. Okay.
One thing before we move on, I noticed Gladstone also asked about if quantization applies to other architectures than transformers. So I will say one quick thing about this. There's stable diffusion.cpp. Which is kind of a similar vein to llama.cpp that supports quantization of stable diffusion. And I've heard very good things about it. I'm not in the stable diffusion field. I don't really look into it much, but I have heard very good things. And similarly, diffusion text models, I believe, are receiving support in llama.cpp recently. So that's an interesting field as well.
Very interesting. Actually, even Jim and I released a diffusion LLM, diffusion-based text model. I actually registered and I in the wait list, and I could go to 2,000 tokens per second. So that was very impressive, which is kind of crazy. But a lot of people, some people said that the bigger, I heard that in Thursday AI, the bigger the context, you may have some surprises. Some people are skeptical about this, but diffusion model can be used for a chatbot as well, and we have the proof with what you just said, and Gemini diffusion model as well. So I don't have the link, but if you have the chance, guys or people, you can give it a shot. Join the wait list, and it's very impressive. Okay, so now we're just going to talk about the two realms of the LLM quantization. Actually, there's it's like, I wouldn't call it yin and yang. It's just like, you got Rolling Stones and you got the Beatles. That's how I see it. So enterprise solution is mostly vLLM or SLG or LM deploy and stuff. And then you have the consumer LLM, which is more the Llama.cpp. So we'll be starting with the enterprise side of it, which is really, really sort of intertwined with the vLLM platform. So I'll let Eldar talk about it. Maybe he can even share his slide. Feel free to do so. We'll talk also about the weights vs activation and throughput latency. I'll have to ask you, like the difference between both activation, because I haven't seen activation on the GGUF side. But feel free to share. If you have a presentation, I can put it on the stage. I think you put it here. Are we good?
Yeah.
Eldar?
Yes,
okay. All
Yeah.
right. Perfect.
Let me just add. So based on there was this question regarding the quantization and the other architectures. Just to add on top of that, so if you guys are actually interested, you can go and Google for Sparsity. That's actually like the repository that we used to maintain before Hugging Face became a thing, where we actually pushed a lot of the quantized CNNs. I think I've seen CNNs here in the chat, like ResNets, YOLO models, and so on. That was actually what we used to work on when we were running models on CPUs.
And CNN is for like images and stuff. CNN is a convolutional neural network.
That's
right?
Yeah, that's right. Yeah,
I have good memory.
Yeah, and basically quantization works just fine there as well. It's just a matter of optimizing for for slightly different layers, but it's more or less the same thing.
Just for the audience, CNN is, for example, used in self-driven cars like Teslas and stuff, right? They can be used to avoid obstacles and stuff like that on Waymo. back in the
I
days,
think
maybe.
anyone who started learning machine learning, I think that's probably the first like set of lessons that they should
Use
have.
case. Okay.
I mean, no, like convolutional neural networks. I think that's the
Okay.
first intro, like before LLMs became a thing. So yeah.
Wow. Okay. That's the 250K, 56K modem version of quantization or neural networks. Cool. Go ahead.
Yeah. So yeah, you asked like regarding the question was regarding the weights and activation quantization. So,
yes.
Yeah. So basically, just kind of like the idea here would be just to show how the architecture looks like and what happens when we are doing forward pass, like when we are doing inference with an LLM. And based on that, we can figure out actually which parts we can quantize. So like at the bottom here, like we always have like the CPU memory. So this is a large memory. It's very large, but it's unfortunately slow. Then on top of that, we have the GPUs, so which have like this high bandwidth memory. And this is what we see when we type NVIDIA SMI on our server. And this is much smaller memory, but it's much faster. And then on top of that, we have the GPU, Astra, and Tensor cores. And this is where actually the computation happens during the inference pass. And this is the smallest part of the memory, but it's also the fastest. And when we want to run inference with an LLM, what we are doing, we are loading the model from CPU to GPU. And this is something we do usually just once. So more or less, this is not that impactful in general, apart from some specific applications which actually care about the loading time. And then during the runtime, what we are doing, we are loading the models from HBM into Tensor cores. We do the computation there. We chunk the layers, like do matrix multiplications and so on, write back the results and repeat. And this is something we do like n times, like because we do this for every single layer in a network, for every like a linear operator. And basically, because we are running this like n times, these are the two main operations that we want to accelerate during the inference, like loading of the layers from HBM into the Tensor cores, right, and SRAM, and actual computation that happens in Tensor cores. So these are the two main operations. For the first one, for the loading part, so the way to accelerate this, so we cannot do anything on the server, right? So it comes with a predefined like a transfer speeds. So it's what we have. So the only way to get the speedups there is to actually reduce the number of bits that we need to load. And that brings us to this weight-only quantization regime, where we just get the speedups because now we have less bits to read through from HBM. The second part is computation part, and this is what I mentioned before. The computation happens in Tensor cores, so the only way to speed up the computation is to use faster Tensor cores. And then if you look at the specs of H100, we see that the BF16 Tensor cores have, like as I mentioned before, like around 2K teraflops, but then the GPUs also come with Int8 and FP8 Tensor cores, and these have like 2x more teraflops. And basically, the way to kind of get the speed up during the computation is to quantize both weights and activations. So we want to quantize both operands that go inside the matrix multiplication operation, and that's when we do weight and activation quantization. And this is how we are optimizing now the computational part of that. And yeah, this is just a note. FP8 Tensor cores are available only on the newer architectures, like a Hopper, H100, H200, and other Lovelace, like L4TS, for example. Whereas Int8 is available on Ampere and all the other GPUs. And yeah, this is the motivation to quantize both operands in case we are in this compute bound regime where we want to get more flops, in a unit of time.
So the weight part, I totally get it. But when you talk about the compute, right? So the compute happens at the tensor core level, right? What is represented by the compute, right? So like I'm loading the weights, and then eventually something called the key values, KV cache, and where is that computation happening in the tensor core once the model is fully loaded, right? And you're doing inference. We're not talking about training. I'm sorry, I'm really focusing on inference today. But so when you're doing inference, your models are loaded. You split them into. You took FP8, and then you're talking about activation here, right? Which is the compute, right? what do you mean by computation intensive?
Yeah, so if we look at the LLM, like how it looks like at the first layer, like the very first layer that we have are the input embeddings. So we have some text, we tokenize the text, so we convert the text into just some integers. We pass the tokens through the input embedding matrix, and this is going to convert every single token into like some n-dimensional vector, right? And then we get like some input batch of our tokens represented in some embedded into this n-dimensional space, right? And this is going to be some large matrix. And then the very first thing that we need to do is we're going to multiply that with the first layer of the network. And the first layer of the network, for example, is let's ignore normalization layer. It's going to be like Q projection, K projection, V projection, for example, or in the MLP part, like up gate or down projection. So basically, all of these layers are represented with one linear operator, which is literally a matrix, like number of input features times the number of output features. And we multiply that matrix with this input batch. And this input batch is called activations. And these are that's the first operand, like input activations. The second operand are the weights. We do the product, and then we pass this to a next layer, right? And then the next layer gets this output of the previous layer, which are now the input activations for this layer. We all again do the matrix multiplication. We pass it on. And this is basically the inputs before we do the matrix multiplication at every single layer. Those are the activations that we are quantizing. Because once we want to do like input activations times the weights, we have to have both operands in either FP8 or int8 in order to leverage these lower precision tensor cores. So we quantize the inputs, and then we already have quantized weights, which we quantized before, for example, and then we multiply them with kind of 2 times more teraflops. And then we pass it on to the next. So basically, it's just the inputs for each layer. We quantize them before we do the A times X operation.
Right. So the weights, that's the loading part, but the computation is your input. It's any prompt that is going to be tokenized and going through every layer until the decoding would happen, and then the end user would have the result, right? So like every layer, whether MLP or any other layers or norm layers, there's a computation happening based on like the embedding that would have been produced based on the input. And this is the calculation that you're talking about. This is the activation side of it. And well, while you can have like a lower bit weights, you could still have full precision activation. Is this what you mean as well?
Yes. So that would be the case for weight only quantization. So I think that's what the Colin will probably tell you more about. So that's the setup where we are not quantizing activations. So like they are flowing in the full precision, and we are just quantizing the weights. And the main caveat in that case is that if we are on GPUs, then we cannot leverage the FP8 or int8 tensor cores, because the inputs are, let's say, BF16, weights are int4. So we cannot use FP8 or int8 tensor cores to multiply them. And that's why we don't get any acceleration on the computational side. But we do get the acceleration for loading, because we are loading less bits.
Excellent. I'll keep this on ice for Colin when he'll start to talk about GGUF. All right, carry on, Eldar.
Yeah, that's basically it. Yeah, I think I can probably stop here. But
great.
That would be the main motivation and the reason why we're doing the activation quantization as well.
Perfect. Interesting. Thanks so much. And obviously, there's the quantization can happen on GPU. It can also happen on CPU and also on ARM, TPU, and many other Gaudi from Intel as well, right? So this is not just on GPU. This is also on CPU and ARM. And I think in your previous presentation, you said that depending on the kind of hardware you have, there is maybe leverage you can use with quantization, activation quantization. Sometimes you can keep it at 16. Sometimes it's better to split it in 2. But it's not always like there's no rule of really rule of thumb. It depends on the case, right? But
That's
you
right.
can
That's right. Yeah.
leverage activation on other infrastructures, other chips as well, right?
Yeah. Yeah, it's always, I mean, it's mostly hardware dependent. So you look at the hardware at which you're deploying your model, then you see the specs. For example, in H100 case, oh, we have FP8. I mean, that's going to be the default choice. Let's go to FP8. But if you don't have FP8 tensor cores, literally the only option you have is then Int8. So it's not like you have a choice. But for example, there is also a question about FP4. If you have B200, if you have B200, then you can actually choose. I can do FP8, I can do FP4. It's more or less like what's the trade-off that I'm willing to accept for my specific deployment. Yeah.
Yeah, and here we're talking about FP4 quants, weight related. Eventually, if the hardware doesn't support FP4 tensors, you could still quantize the weights.
You can quantize the weights, yes. You just need efficient kernels, which are going to be able to unpack properly the packed weights for the inference. But you will not be able to get the computational speed up from faster matrix multiplications because you don't have FP4 tensor cores on that specific GPU. If it's not Blackwell, of course.
It's relative, right? When people say fast, what do you mean by fast? Faster load-in or faster computation? And sometimes, even latency and throughput are two different things, and people sometimes confuse them. I don't know if you can have if you can talk about. Maybe we can talk about it later, but basically, which one is memory bound, which one is compute bound, for example.
Yeah. So the main distinction there is it's that specific a threshold, whether something is memory bound or compute bound, really depends on many factors, like number of queries per second that are hitting your deployment, size of your model, size of your GPU, and so on. So that's really something that usually you should do proper benchmarking for your model. So this is my GPU, this is my model. And I can now simulate, these are the workloads that I expect to get, like the input size, this many requests, and then you simulate that, and then you benchmark, and then you see actually where this flip happens. It's very hard to tell it upfront, oh, you will be in this or that regime. For some cases, it's easy, just when you say, oh, it's a very small model on a very large GPU, or I have just maybe 2 requests per second or something like that. That's more or less indicates that you'll probably be in this memory bandwidth bound regime. Whereas if I am deploying, I don't know, DeepSeek, and I'll have 100 queries per second coming in or something like that, then most likely you will be in this other regime, which is bounded by compute.
Gotcha. All right. Now it's your turn, Colin, on the hot seat. Talk about GGUF, about the LLMs for the people, not just for enterprises. So I don't know if you want to share any.
I don't think I have anything. I'll see if I can get one while I go.
Okay, just for example, let's start about the Llama.cpp sort of event or a momentum. Do you have any sort of background on how it was unfolded? And obviously you started late 2023, but
yeah, so I was there towards the end of the initial acceleration. I kind of had a little bit of vision on it at the time. Georgie was hacking away on his MacBook trying to get the recently leaked Llama code running on it, and got something working that seemed to perform reasonably well. And the particularly interesting part about it was that at the time, obviously, the Mac inference engine, that wasn't a thing. There was no way to run language models locally on a laptop. That just, people weren't doing that yet. And so that was quite the revolution that he was able to figure out how to do that and get it running in a stable way that was, relatively performant and was similar to what was being output by enterprise. Obviously, since then, it has expanded tremendously. Obviously, and from well, based on what we're here talking about today, quantization was one of those main ones that kind of pushed it forward in the consumer field, at least. And so being able to quantize the model down to smaller sizes that had Q40, Q80, things like that, and those represented 4 bits, 8 bits of quantization, so that it could run on load up into significantly smaller GPUs, because that's typically what the issue is with consumer hardware, is that we don't have a lot of RAM. You look at an H100 that's got 80 gigabytes of RAM. That's a huge amount, can load basically anything onto it. But then you look at what they have on the consumer side, even the most expensive one you can buy now, the 5090, like $3,000, $2,000, it's only 32 gigabytes of RAM still. That's like less than half of what you can get on an enterprise card. So it becomes tricky to load, these, particularly, the 70 billion parameter models. It's basically impossible in any other way. And the other thing that GGUF does nicely compared to some other libraries that exist is that it allows for partial offloading. So you can run most of the model on your system RAM, but then have those activations that Eldar talked about happen on your graphics card itself. And this still provides a massive acceleration versus just running everything on a CPU. So like for myself, I have many things that I need to run with GGUF, and I'll just leave the entire model on system RAM, but just throwing the calculations onto my 3090, which only has 24 gigabytes of VRAM, it can't do a whole lot. It accelerates, I think, like 2 to 4x the speed of calculations. Wow. So just being able to do something like that to load up massive models without having an enterprise level GPU is definitely where its claim to popularity came from.
You're loading the model in CPU RAM, and you offload the activation or run the activation in your GPU, right?
Exactly. Like the KV all runs there. And so that's where I get my acceleration from, because obviously I can't load particularly large models, but I need to for iMatrix, which we'll probably get into later. Where was it? Oh yeah, so the initial quantization schemes, the blockwise quants that you can see on your screen, they were relatively naive, all things considered. They performed fine. They were surprisingly good, honestly. Like going to Q40 and still maintaining a pretty good amount of quality was probably shocking at the time. But then came the K-quants, which I think are really what make Llama.cpp. Yeah. So and I think it's probably good to point out at this time, you can load up my image, the IK Llama.cpp, because this is the I always forget 𝐓𝐞𝐜𝐡.
𝐓𝐞𝐜𝐡. Yes, like who's that guy, by the way? Yes, 𝐓𝐞𝐜𝐡. Ivan. I mean, yes. Like Eldar is like W in Eastern Europe means V. Like I1 is Ivan. Okay, cool. So yes. Ivan 𝐓𝐞𝐜𝐡. Who's that guy?
𝐓𝐞𝐜𝐡. That makes a lot more sense than what I was pronouncing all this time.
Yes, who the hell is this guy?
I mean, it's still a great question. All I can really for sure say is he is a genius in the field. He does a lot of incredible stuff. He still maintains a fork of his own right now for Llama.cpp. That is kind of where it's almost like his testing grounds, where he just commits all these wild things. He's got state-of-the-art quantization available here. But in the past, he worked on Llama.cpp directly, and he introduced this concept of K-quants. He introduced iMatrix. He introduced the iQuants, which came after the K-quants. So K-quants was basically, so the way that Llama.cpp quantization works is it defines these blocks in order to group weights together to be compressed together and have a shared scaling factor. And that's why we get like better than just straight up quantizing to 4 bits. We are able to share some of the information across multiple weights in order to maintain additional quality. And so K-Quantz did this even more so. Like it had quantized scaling factors, it had super blocks and regular blocks. Like it's honestly, it's wild to even conceptualize. And then
you're right, man, because I've been reading a lot before writing my blog. By the way, I'm just going to share to the audience the blog that I wrote. So I've been reading in Reddits. I've been reading in GitHub. So he had like an explanation of the perplexity of every type of quantization approach by bit and stuff. And then at the end of his explanation, he said, I should have a documentation around it, but I don't have time.
Yeah.
That's literally what he said.
So
this is
very
how hard to find like information or like background information about what you're talking about, super blocks and especially the K-Quantz. I found out that K means key means. So maybe I'm wrong, but that's apparently what it means. K-Quantz means key means quantz, right? So it's actually a smart bit allocation, right? As you said, it's not like just one bit, but like within one block or one super block, you may have like some weights that are like 4 bits, others full precision, and then others like 6 bits and stuff like that. And then it's a sort of like an average. When you say like key is like a Q4K, it's like an average 4 bits, but it's not totally 4 bits for every weight. Is that correct?
Yeah. So it groups all the weights into so for Q4KM specifically, it groups the weights into blocks of 256 weights. So it starts with that, and then it defines some it defines some minimum values so that you can keep track of what the minimum in that weight block is, some scaling factors, and then it actually quantizes the weights themselves. And then it can use the combination of the scaling factors and the minimums to retrieve similar to the initial weights and maintain the relationship between all of the weights within that block. And so based on so there's the actual weights themselves are 4-bit. Then there's the scaling factors, which are kept at, I believe, 16 bits. Excuse me. And then there's the minimum values, which are 6 bits. And altogether added up over, excuse me, over the 256 weights in the block, you get 4.5 bits per weight effective quantization. And so that's why, like, the number 4.5, it doesn't sound right. Like, how do you quantize to half a bit? Well, it's because it's an average over the entire super block and then over the entire model if it was all done to Q4K.
Right.
Because Q4K, there is a slightly unfortunate naming here where, so Q4K is a type of quantization that's going to 256 weights per block and defining the scaling factor and all that jazz. Q4K_M is a quantization target of an entire model. So that'll probably end up being, yeah, exactly. It'll be a little bit more than 4.5 bits per weight because some of those weights, some of the layers, some of the weights will be quantized to a slightly higher level because part of it's like they found, the feed forward net down projection. We actually do a huge benefit if every so often we quantize it at a slightly higher rate rather than keeping them all at Q4K. And so that was all done with experimentation. Yes, I should be able to pronounce that name. Sorry, I just noticed the comment.
That's funny. Okay, yes. Fair enough.
No, you're right. So there's this unfortunate naming in that sense where, Q4KM is something different from Q4K, but it does primarily use Q4K
as an approach.
Exactly. Yeah. So most of the weights within a model will be quantized to Q4K. And then a
Okay.
few of them will be left at different levels because people found over time that it works better to leave some of them at different levels.
And to your point, I just want to maybe like our audience, just for those who don't know, because I didn't know back in the past before writing that blog what scaling factor means. So if like, would you correct me? So as I understand, scaling factor is like when you have a sort of a skewed value in your matrix. And then at some point, like the scaling factor would be something like that all the weights will be sort of multiplied by, so they can have like not a too high or too low value, right? So this is like you're sort of like a mean value of all the weights, just because you have that scaling factor, you multiply everything by that scaling factor, and then your matrix will be like okay, because
it blows it up like to the original range, basically.
Got you.
Yeah, it's like a linear mapping. If you imagine like the unquantized weights can be in the range minus 100 to 100, and you want to quantize them to minus 10 to 10. So you're going to be using a factor of 10 just to kind of like, it's like a linear mapping to map it down to a smaller range.
Yeah, exactly that.
It's like you know what? Like I have a music background a bit, so it's like sometimes when the bit rate or the frequencies of you go from WAV to MP3, sometimes some frequencies are not really useful because human being cannot hear it right in a song or a track. So when you compress, at some point they get rid of all those blanks somehow,
right?
And they focus on where like in sort of graphic or like temperature picture, was like a thermal view of it. It's like, where is all the concentration? This is where I trim, right? And all the like the blank, I remove it more or less. Is it more or less what it means? Like, would you like sort of draw a parallel between the two? Because when I see that, I'm like, oh, you know what? Like music was like that too, because at some point, like some frequencies on the track are not heard. That means it's not a big deal for a human being if like you remove those frequencies when you compress the track. But maybe I'm divergent here. But
yes and no, in the sense that quantization will reduce noise in general. So you will have fewer of the outliers that would potentially be something like you're talking about in music, where like, you might lose a really high pitch for one part of the song because it just wasn't able to fit in to the envelope of how much you were quantizing it. But I wouldn't say it's necessarily targeting that in a logical sense, at least not for GGUF. There are other ones like, for instance, AWQ and Llama v2, now v3. They will purposely go through and find which weights are more important. So it's like, for instance, if there was a part of the song that had a ton of music in it, like way too much information, but it was kind of important, like it made the song. What these ones will do is that they'll quantize other areas a little bit more to leave this area a bit bigger. That way, exactly. So that way you can kind of maintain the important section a little bit nicer, while sacrificing the less important sections a little bit more.
Got you. And we have one question from one of the from the audience. Maybe the quantization naming at some point it was confusing for some people, but Q4 means 4 bits. K means k-mean, for example, and then you have the size when you said like how much do you want, and then you have S, which means small, M, correct me if I'm wrong, means medium, and then L means large, and now they have XL, UXL, because these are new, really fresh. I'm used to SML. That's all I knew back in the days, but now like they have UXL, XL. So am I correct? This is more or less how it's...
it's more or less, in terms of like the official ones, there's really only the SM and L. And even at that, only Q3 has an L. Honestly, it's probably at the point where it would be nice if we could go through and rename everything, but it's too late. Like the ship has sailed. It's just happened, and it is what it is. But yeah, so it is confusing in that sense. It's difficult to find the resources. Like I try to do my best to explain it, but it's just hard. It's just they were named when the project was just kind of flying by the seat of its pants, and no one went back and tried to fix it, because why would you?
You bet. You bet. Oh, well, all I know is at some point, like the sweet spot for anyone who wants to use more or less small models, quantized models, the Q4K-M is like really the sweet spot for people that want to try it for the first time in terms of, you know, quality versus size and performance. That's what I usually use. I rarely go to L. It's mostly M. If depends on how much gigs you have, obviously, in your hardware, right? But mostly you can, like, your key M is cool. Q4 key M is like, you know, you can start with that and then see where you can go from there for sure. So next, I think there is also more because we have extreme quantization now. It's not just 4 bits. It's 1.58, and they call it 1 bit, but it's obviously more than 1, right? Because it's tertiary. They call it ternary and tertiary bits, because it's not just 0 and 1. It's, was that -1, 0, and 1? The values apparently
that's the real ternary,
Ternary, okay, ternary, right? So we have models like Bitnet that are like 158 bits, and they claim also that, you know, they're faster on CPU on ARM than Llama.cpp. Obviously, always compare yourself to like the incumbent. That's very convenient. Lower memory and computation, they use that in fine tuning. So I'm not like, there's a slide where like we really, you know, show all that exists, but this is also possible. We can go as low as you know, as 158 or 2 as well, right?
Though there is a caveat to this specifically, is that this is not quantizing an existing model, typically speaking. This, I believe this is training a model with this Bitnet technology and then running it at full precision, which happens to be 1.58 bits per weight.
So what do you, when you read the Llama 3 8B, 158 100 billion tokens? Yeah. Did they retrain Llama, or did they post-train it? What did they do with it in order to call it like a 158 bit?
I imagine it's some post-training, hence the 100B tokens, but that's a fair point that I should look at before I make my claims.
Yeah, because like it's like a fine-tuning technique, maybe. I don't know where to put this. Is it a quantization, or is it a fine-tuning? Is it something that comes on top, or like the usual quantization where like you don't touch the content, the parameters, right? Like you touch the bits, but nothing else. But it seems like these Bitnets frameworks are doing a bit more, touching the weights, like the parameters, the embeddings, the dimensions, stuff like that.
I think this comes like kind of in between. Like after you do the training in the full precision, you get all of the benefits of like the full precision model training. Then you do like something like, it's not like a form of like a QAT, like quantization aware training, where you dedicate a subset of tokens, for example, in this case, 100B, and then you just like do like additional training stage where you simulate quantization during training. And then you have to do some tricks kind of to stabilize it and so on. But then you kind of benefit from all the knowledge you learned during pre-training. And then you end up with like a quantized model in the desired scheme that you impose. And this usually is kind of like in between.
Oh, it's not like a pure quantization. It's quantization
you get
on post-training.
Yeah, I mean, they're like two techniques here, like quantization aware training and post-training quantization. Post-training quantization is what we are all like doing here, like all these like Q4 and so on, Q5, and all of the quantization we're doing in LLM compressor. But kind of QAT is like more expensive one because now you need training infrastructure, you need a training data set, you need to like stabilize the training, tune hyperparameters, and so on. But the benefit is that you will get quantized model at the end of it. You don't need to do PTQ, what we are doing here. And yeah, this is kind of a little bit harder to do. But if you have resources to do that, you should more or less do it always, because you should probably always end up with a like slightly better model than what you will get with PTQ. It's just like you put more compute on top of it, and yeah, if you do it right, it should be a really high quality quantized model.
Interesting. But what do you think is the data set? Like, is it like a big data set, or like just like something to run on top? Is it like distillation or stuff like that, or?
It really depends on what the target is. Like, yeah, like you can do QAT specifically for specific tasks. That's something that we used to do before. For example, you have Bayes pre-trained Llama model, and now you want to fine-tune it on some instruction following data set, which is something you can run on maybe 4 or 8 GPUs, something very reasonable. And that's a set framework where you can attach QAT on top of that and immediately fine-tune a model on the target task with QAT, and you end up with quantized model fine-tuned for that data set.
Right. So QAT.
Yeah, this.
QAT, like just for the audience, means like a quantization aware training.
Yeah,
is
that's
that
right.
What that means?
Yes,
okay,
yes,
cool.
that's right. You basically simulate quantization during training. So during the forward pass, you kind of fake quantize everything so that your weights are kind of doing that. But then during the backward pass, because quantization is not differentiable operation, you kind of do it in the full precision. So you do full precision backward. And then again, you do forward pass with kind of fake quantized weights, and then you update everything back in the full precision. And that's how you go back and forth. Yeah.
That's insane, man. Fake quantization. Fake quantization.
Yeah, because you want to simulate that to a model, so that the all of the activations and the loss are kind of tuned for this quantized setup, so that the outputs are not in full precision, but actually they have some errors from quantization.
Okay, so but in terms of accuracy, like, would you lose some accuracy in the forward stage, or?
I mean, it's so in terms of the accuracy versus just doing it like as we are doing it like a PTQ.
As is.
It's either the same or better. So that, at least if you do it right, it should never be worse than PTQ.
Okay.
But now, given that we have methods with like these like PTQ tricks, like where we do like very efficient like 4-bit, 8-bit quantizations, where we lose 1 or 2%. It's now a question of whether it makes sense for your deployment actually to do that. Do you really want to put that many resources just to get 1% higher accuracy? So yeah, it really depends.
Gotcha.
But if you do it right, it should not be worse than doing PTQ. Definitely.
Interesting. Okay, so one other question I had for Colin is I think when I was reading about quantization, especially GGUF, I was talking with the maintainer of the Python version of Llama.cpp. And so we were discussing, I was reading stuff on Reddit. Obviously, as I said, like, what's his name? Ivan 𝐓𝐞𝐜𝐡. He didn't want to document anything. So at some point, there was a confusion. The documentation, or even Google, would tell you that GGUF, which is a format, came after the GGML, right? GGML means Georgy Garganov ML, machine learning, by the way. That's what it means, the acronym. But the tensor library is GGML, as I understand, right? But then, like, all the documentation is saying GGUF is replacing GGML. And it's a format, it's not a library. And then a lot of confusion was still to this day is present around the naming convention, what those name means, like what is the library and what is the format, right? Can you help a bit differentiate between these two? Like, what's the relation? Which one is like truly the format? Which one is still a library only?
Yeah, so this is one of those ones that was also an unfortunate naming convention that was caught early enough to and even then caused a lot of controversy at the time. But it was caught early enough to kind of correct the path. So initially, models were just saved with the .ggml path, and they were called GGML models because it was using the GGML library. But then partway into it, yeah, and or .bin even, like people just like called them whatever they wanted. But then a couple years ago, I think now, there was a push for a more standardized file format, and this GGUF is a unified format, I believe, is what the UF is.
Yes.
Came into
GPT
creation. Yes, and so it kind of what it did was it standardized the way that the models are saved and loaded in very important ways. Like we can see there's a ton of interesting stuff that's come from it, like Hugging Face. Now if you go onto a GGUF page, you can explore the model itself and like the information about it, all of its values, what the layers are quantized to, like that's visible to you in your browser because
the blocks, the super blocks.
Exactly. Because GGUF is this very standardized format that is now being used to save all of these models. And so it really unlocked going forward a much easier path, especially when it comes to adding stuff. Like there's been times where they need to add extra tensors to represent the rope scaling, for instance. And that's like kind of trying to extend the context of the model. That needed to be saved within the file itself. In GGML, it kind of just would have been put in somewhere and hopefully pulled out something in the right place. But GGUF, yeah, it standardized it. It made it maintainable, and it was a very important step taken. That's honestly a lot of the Llama CPP's relatively recent history has been around these painful refactors that are critically important for the health and future of the platform. And that was one of the earliest ones, to my memory at least.
So can I say GGML is a library?
Yes.
Still? Okay.
Yes. And it is still a maintained format library.
Say again?
It is still, like, if you go to it's called the GGML organization now, their GitHub has the tensor library still, and it's used in Llama CPP.
Right. It's still used it's a core library within within
it hasn't gone away.
Llama CPP. Right. Yeah. But back in the days it was GGML library plus format as well.
Exactly. Yeah. So it had that confusion and the crossover that didn't make sense actually, and so they refactored it, much to the dismay of many people, but it now, and in fact, so much to the dismay, there's a fork of Llama CPP called 𝐂𝐴LT-CPP. And it is more than just a fork. Like they have added a lot of their own stuff there as well, and it is quite a nice platform for running inference. But they have maintained backwards compatibility, I believe, even all the way back to the GGML, like original files. Like you can still load them up on the. It's caused them crazy headaches. I keep telling them to stop doing it, but they have the backwards compatibility for years. It's crazy what they do over there.
That's sick. I got a question to Eldar though. So because I've been asking this question in the vLLM Slack, to be honest, and I was always wondering, what is stopping the vLLM community for like leveraging something like GGUF? I'm not saying like copy paste or something, but like being inspired by something like that instead of having like a clutter of files from Hugging Face every time you need to load a model with the config, the .json and all that stuff. Like what is keeping the community, the maintainers, for adopting something like that would just make life easy?
So right now there are two things there. The first one is like, if you want to run GGF models in like vLLM, you can actually do it. I think there were like some like community contributions to actually enable.
It's experimental though. It's like
it's still experimental. It's probably not the fastest thing that you would get, but at least you can run it if you really want to. But there was like the same problem that Colin just explained also happened in the quantization world when GPT-Q, like that was like the first kind of one of the first algorithms which actually like went viral, was like able to do the int4 quantization for specifically for GPUs, came with like very good kernels to run that on GPUs. it used one format like to save the quantize, because when you're quantizing to int4, you have to pack your weights, right? Because you have like int4 weights. Now you have to pack them into like for example, like 16-bit weights or something like that. And then 𝐤𝐸TQ used one way of packing this. Then at the same time, there was bits and bytes, and they used different formats for packing. And then I think 𝐴WQ came with completely different now format for packing, and they all had like different formats to save the quantized models. And then when you're actually writing an inference kernel for 4-bit model, you now have to consider all these different versions of like quantized models, because now you have to know how did they pack so that you can unpack as very, very efficiently. And that all like caused a ton of confusion, because sometimes you take 𝐤𝐸TQ model, you would load it up, you would run it, you would get like garbage outputs from a model, just because the unpacking wasn't done in the way that the packing was performed on the 𝐤𝐸TQ side. And actually, we created the kind of like a standard for this called compressed tensors. This is now like a standard which Hugging Face also adopted as part of the transformers, which actually specifically like sets the standard on how to save quantized weights on a disk. And now it's also been adopted by vLLM, and now that's what, for example, also LLM compressor is using. So now whichever format we use for quantization, FP8, int8, int4, weights, activations, blah, 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 there will be a unified format to save it. It will be compressed tensors representation. And then vLLM will know, or Hugging Face transformers, they will know exactly how to load the model, which bits represent like assigned bits, which represent weights, and so on and so forth. So yeah, there was also a lot of confusion there. And I guess we are kind of trying to get around that with the compressed tensors. Yeah.
It's about time, man. It's about time, because you're gonna have a lot of users and adopters, so it's time to converge to something really global, universal.
It was really frustrating period, especially for academics, because when you want to reproduce like results from a paper, you just want to run it as quickly as possible just to get some numbers and move on back to your projects. But then you get garbage output, and then you start wandering around what's happening, and then you spend 2 days just like trying to get the proper replication of that.
Woo.
Yeah, it was a huge headache. Yeah.
So LM compressor. So go ahead.
I want to say one thing. First of all, safe tensors. Very happy that format exists. That's a nice standardized format. Again, similar thing where you can load it up in like the Hugging Face view and see everything about the models. And I feel like there's this idea of, why do you have config.json, tokenizer.json, tokenizer config.json? Why don't you just have one single file that users load up? And my counterpoint to that is actually like, look at the commit history of what you're showing right now. Add extra tokens, update config.json, things like that. Like, you can't do that in GGUF. I love GGUF. It's great. The models that they create are great. But editing it after the fact, after it's made, it actually becomes, for me, in a lot of cases, more efficient for me to just delete the model and redo it. Because my automation script is like, it's nice and set up. Like I can just click one button and it goes. But if I need to update the chat, the chat formatting, the chat template, I have to download the model, run a script, and then re-upload the model. Like it's a hassle. Like every single quantized version, if I upload 15 of them, I have to download each of the 15, run the Llama.cpp script that takes out the old one, puts in the new one, and then re-upload that whole file. So there is a give and take. Like, yes, it is simple, especially for an end user. I love the experience for an end user to say, here's my one file, load it up. But in terms of like development and trying to be, especially like the enterprise side of things, I can imagine as well, like being able to discreetly change individual parts, edit your tokenizer config.json manually, and just upload that one line file change. Like that's hugely beneficial from a model maintainer perspective. So there's definitely a give and take.
Yeah, I totally get it, because from the end user standpoint, we like having like one model to load, and especially if we could even quantize a model. So like I'd rather quantize a file than quantize a bunch of files. Maybe I would lose one or forget, or I'll make mistakes and stuff. But if it's one file, I'm sure everything is in there. So if I do inference or quantize, I have everything I want. I wonder if like there is no like a middle ground between these two. I know that LM compressor has like a recipe, so you just tell it everything, maybe chat template as well. I don't know, Eldar, you can confirm. But in the meantime, like even for GGUF, you can do that in a CI/CD pipeline, and so like you can deploy every time there's like a meaningful patch, and like when you modify a small thing, if it's like worthy of a new deployment, fine, and then like you just run the pipeline and you will have like a new patch, or there's a specific changes that would warrant that kind of update of the GGUF instead of like creating a new one for every small change, because people are not going to die. The earlier version is also good. It's just that like you're improving it, you know, along the way.
Right. What I mean more so is like when I have if I create a repo for a model and then I find out that the chat template is wrong, I'm just going to run my script a second time from scratch and upload it to the same repo to just replace all the files in place, because that's easier for me than manually going and downloading each individual file, editing it, re-uploading it. Like it's such a hassle to have to, like, it's basically a black box. Like, while there's a lot of visibility into it, editing it is not easy. So that's where the trade-off comes from.
Got you. Obviously, we have Ollama, we have vLLM, we have Local AI, we have LM Studio. I guess like you've been working with. Can you tell us what you've been doing for LM Studio lately in terms of quantization?
Yeah, the main thing is like if you go to the LM Studio community on Hugging Face, the GGUF models are the ones that I had been creating and uploading. They've also got MLX going on now from someone else, so they're just kind of maintaining a library for LM Studio for the users to have, you know, a list of basically these are high quality known working models. You can download anything you want, but if you download from here, you're going to have a good time.
Nice. And is like, I know that Ollama, for example, you can download directly from Hugging Face. Is it the case for LM Studio as well? It's like you can like just put the like a Docker image kind of name in, and then it will just load it for you.
Yeah, so they have like the CLI similar to Ollama, where like you can say I don't remember exactly. LMS, like LMS pull and then the model name. But then also the LM Studio is designed more around the graphical interface.
Yeah.
So you would go to the model download. You can find anything from Hugging Face there.
Interesting. Okay. So one other question is, like, how long does it take to quantize a model? Let's say two examples, like Llama 3.8b and Llama 3.70b. It's like how long it would take based on your hardware to quantize a model. Couple of hours, a day, like for people that want to try it.
Yeah, fair.
How would you start?
Well, so there's a couple of caveats here. First is that I upload 15 sizes for each model that I upload. So like my quantization process takes a lot longer than what an average quantization process would take for a single. Like if you had a specific size in mind that you wanted to create for, that would be much faster. Like for a 7 billion parameter model, you would take, a couple minutes to download, maybe 1 minute to convert, and then another minute to quantize, and you're good to go. Where the complication comes from also is with the concept of iMatrix, which is basically a way of kind of edging the model a bit more towards higher quality. Like it won't astronomically change the quality of the model, but it will make it slightly better, especially the lower the quantization target is. So like Q4KM, it's a negligible effect. If you're making a Q4KM model, you can have it done in a few minutes if it's a small one. If it's a 70B, it'll maybe take you half an hour max. If you
what hardware are you using, by the way? It's like just
so for my own stuff, yeah, I've got an AMD EPYC 7702. So that is a 64-core server CPU. But then,
okay.
Yeah. And then I've got it paired with a 3090. So Llama.cpp, unless you're doing iMatrix, you only use CPU for the quantization process. It's all done entirely on the CPU. And so from that perspective, it's very nice. And there's even a Hugging Face space called GGUF GGML my repo, I think it's called.
Nice.
GGUF my repo.
Well,
GGUF my repo.
Yeah. You can copy it into the chat, so I just shared just for people that are interested. Cool.
And so the idea being that, I have to connect my YouTube. I'm just gonna paste it on YouTube that I already.
Yeah, cool.
And so you can go there and get a quantization of any model that you find. Probably not any model. There's probably a size limit on them because they do get quite big these days. But most models, you can just go to there and have it create the quantization for you, which is nice.
Nice. Well, you quantize online or something? Is it?
Yeah, it uses a Hugging Face space to perform the quantization within, because honestly, it doesn't need that many resources, especially if you're not using iMatrix, and especially if it's like a relatively like below 30 billion model. Like it's actually pretty non-intensive, which is nice. Okay,
good to know. Because I got a friend who told me it took him a day. So I don't know what hardware he was running. But yeah, so he told me it took me a day. So maybe I'll talk to him again. Tell me again, what were you using?
What was he doing? Because iMatrix can easily take a day.
Weren't you actually rendering some video and say it's like Adobe Premiere Pro or something?
Yeah.
I think Eldar with LLM compressor, like what's the average time it would take based on?
It's very similar, except that in our case, usually you do need GPU. This depends more or less on which quantization scheme you want to do. If you're doing FP8, usually FP8 is very accurate quantization. So usually what you need to do is just round to nearest. So we don't need any calibration data. If you want to do int8 or int4, then we usually employ like algorithms like 𝐓𝐞𝐿, smooth quant, and so on, which do require passing calibration data through the model. And
if sampling you're passing or something like that?
Yeah, you take like a set of input prompts and then you pass them through the model.
Interesting.
And all of these quantization algorithms, what they're doing is like they take a input batch, they pass it through an unquantized layer, and then they say, okay, now let's quantize this layer such that we reproduce the outputs that the unquantized layer produced. So it's kind of like you're minimizing mean squared error between the outputs of unquantized and quantized layer. And in order to do this, like a 4 pass through a layer, you actually need a GPU. But yeah, the runtime is more or less the same. It's like order of a few minutes. If you're dealing with models below like 30B or so on, 70B. If you're doing like, I don't know, this 𝐂𝐞𝐜 or DeepSeek R1, then it's like
this one is
that one is the beast. 100s for a couple of hours.
Yeah. What kind of hardware you usually use? Is it like 800 or like can you go down L4 or something or?
Yeah, I mean you can. Yeah, because the LLM compressor has a way of quantizing these models when you need calibration data to just load one layer at a time. So that means that you can do it on GPUs with very like, I don't know, 24 gigs and something like this. But yeah, if you scale it up to like DeepSeek and so on, then it gets a bit tricky. You need more GPUs. You need more RAM.
Got it. Well, DeepSeek they have MOEs, so you may quantize per expert as well.
Yeah.
I'm just shouting. Like, I mean, I have no idea if it's.
I mean, we actually do that. We are quantizing experts. Yeah. That's how we quantize MOEs. Yeah.
Okay. All right. Perfect. Colin, do you have a calibration too with the?
Yeah, that's what the iMatrix is. So basically, it's a corpus of text that runs through the model either at full precision or you can quantize it before doing it in case you need to save a bit of space. And then it measures how many times each weight activates. And then during the quantization portion, basically there's a few different like scales and minimums that are tried as the quantization happens. And we try to minimize, I say we, I don't participate in this. They try to minimize the loss difference between the initial weights and the quantized weights and then going back. And so with iMatrix activations, it adds an extra factor in. So minimize the loss with relation to the importance of the weights. And so that's why iMatrix has the ability to bump up the quality a bit. And that's why at high precision, it doesn't actually do much of anything because you're not introducing much loss to the model to begin with. So iMatrix won't do much if there wasn't much issue to begin with.
Gotcha. Well, but you're not having inputs like samples that you throw in at the model during the quantization.
Yeah, it is a precursor to the quantization. It's so you run it on the full weights, create this iMatrix file based on a corpus of text acts as the input to the model, and then you save that information to reference during quantization itself.
And there's one thing that everybody's confused about is people think IQ means important metrics.
Yes, that is
right.
Another unfortunate. Both it's unfortunate for the fact that it starts with an I. It was released around the same time, and most of the I quantizations require iMatrix, but that's just because they're very low precision. And so Llama.cpp, the scripts force iMatrix below a certain level of precision. And that's why, so they kind of got this relationship of people thinking iMatrix equals iQuant. No, not really. They one needs the other a bit more than the other sizes do, but no, they're completely different concepts.
You can still have an IQ quantized model that is not using iMatrix.
Yeah, so there's only a few sizes, like the IQ4 is fine to do without iMatrix. IQ3S, I believe, and then I think XS and maybe XS is where you start to need iMatrix. I think caveat to that is that they do benefit, like even IQ4, I think benefits more from iMatrix than like Q4KM because it does do some different kind of concepts. The IQ4 is also an unfortunate name because it's not really the same as the other iQuants. It's really just a non-linear quantization. So instead of just mapping to straight values, it has an array that goes from like -127 to 127 in a non-linear way, because they found that if you quantize onto this non-linear buckets, you can actually find a more reasonable relationship to how model weights are actually saved during training. And then the other iQuants, I won't even get into them because they're black magic basically. But I guess in a sense they're similar because they have this massive array of values, and the weights themselves are actually mappings into that array rather than being like, you're not actually quantizing the weight. You're taking a group of them and you're mapping it into a section of the array that most accurately represents those weights.
Wow.
Yeah. Okay. So that's some more magic from Ivan. Like it took me honestly a full day or two of reading through the code, reading through the PRs, and just trying to figure out what the hell is going on here.
Oh my.
It's fascinating stuff.
Yeah, I don't want even to dive in further. Just folks, so you know that IQ doesn't mean iMetrics. Right? Yeah, it's like I want to set the record straight here. You heard it here. IQ doesn't mean iMetrics for sure. Interesting. And then, well, there's something around. Before there was a question about LoRA. LoRA, right? So like somebody asked a question about LoRA. So we have a quantization for LoRA as well. Again, for people that don't know, LoRA is for fine tuning. I'm not really into it. Mostly like diffusion models use a lot of LoRA. I'm not sure if like language models too. Maybe if you fine tune as well. But can you just give me like a brief explanation of a LoRAQ and why it's used and why it's useful eventually in fine tuning? Eldar?
Okay. So yeah, basically LoRA is like a way to do very efficient fine tuning of even LLMs. I think it was first proposed for LLMs and then people ported it over to other architectures. And the main problem was that when you're fine-tuning an LLM, you need a very large amount of the GPU memory to store all of the intermediate activations. Because when you're doing backward pass, you now have to like compute the gradients and so on. So what people figured out is that if we take the model, we completely freeze the model weights. So we take Llama, we freeze all of the weights, and then we add these low rank adapters on some specific subset of layers. And we just like do standard training, but we only train these adapters, which are like a low rank approximation of the original weight matrix. This is very cheap to run because now your entire like a main backbone model is frozen. So you don't need to store all the intermediate activations for that and so on. You just need to kind of optimize for this small like adapter part. And this is how actually you can do like Llama fine-tuning on Google Colab GPUs or something like that. Very efficient, very good. But yeah, there are kind of still a lot of discussions on what's the quality of the models once you do the LoRA. You know, for some applications it's good enough. For some applications it's not. There's like a very good paper from Databricks which actually shows what LoRA is actually doing, like on a larger scale. Sometimes you forget some knowledge you learned during training. Sometimes you learn a bit more of the new knowledge. But yeah, it's still a trade-off. I don't know whether you're willing to accept that lower costs for fine-tuning, but yeah, then you don't get as good model as you would get if you're doing full fine-tuning.
And LoRAQ is just quantizing those LoRA.
Yeah, basically just a quantized version of the same story. Yeah.
Right, but the rest is working as usual.
Yeah, more or less. Same concept. Yeah, they're just same concept, just some other tricks to make this a little bit stable for fine-tuning, because whenever you're dealing with quantized weights, like the stability of training is like something you always have to consider. Yeah, that's more or less it.
Got you. And since you're here, I'm going to ask the follow-up question, which is the sparsity in quantization, because like a lot of people hear about distillation, sparsity, and maybe you can just tell us like with few words briefly, like what they mean in LLMs and also in quantization.
Yeah. So sparsity is like one additional technique to like reduce the size of models. And here we are reducing the size by actually eliminating the weights. In quantization, we are not removing any of the weights. We're just like reducing their bit width. Whereas in sparsity, we are completely like taking them out of the network.
How do they choose the weights? Like which weights to reduce? Like you split it in two, like convert them into zeros. Like how do you choose the victim?
You convert them to zeros. That's the goal. So you want to convert them as many as possible to zeros. But then the entire game is like, how do you find which ones should go to zero? And there are like some algorithms for that, like a sparse GPT, which we've worked on and so on, which are applying more or less the same tricks as we're doing in quantization. So you're trying to estimate the importance of specific weights in a layer, and then based on that. Yeah, the entire iMetrics story is very similar to like a GPTQ idea, where you're kind of, at least in GPTQ, you're just estimating like a hashing of a specific layer, but it's usually like, in the end, it ends up being like a huge like importance matrix, which tells you if you quantize or if you remove the specific weight, this is how you're going to affect all other weights in the network. And then based on that, you say, okay, I can quantize or I can remove this weight based on that. But it's more or less the same story, just kind of implemented in a slightly different framework. Yeah, and for sparsity, it's the same. It's just like we're trying to set them to zero, and we see, okay, if we set these weights to zero, what's the effect on the accuracy of the model?
So it's not random.
Yeah, it's not random.
Okay, they're not shooting out weights.
Yeah,
and then like, you go to
zero.
Be
really bad. Yeah, yeah, that's gonna be really bad. Yeah.
Nice.
For GPUs specifically, the only choice we have is 2-4 sparsity, because that's what the NVIDIA offers us. Like they're like 2-4 sparse tensor cores, which means that for each block of 4 consecutive weights, you have to zero out 2 of them. So that's what the 2-4 means. And if you apply this format, then you can get like 2x faster forward pass on NVIDIA GPUs. And that's, for example, what we are usually doing.
is it done at like kernel level? I'd say like at hardware
It's-
level, at tensor level,
So-
or
Yeah, so the sparsification process happens in the same way as the quantization process. You load one layer, you pass through some calibration data, you have this importance matrix, you figure out which ones to zero out, which ones to keep in the original form. And then once you save the model, you want to run it. And then that's the way. So like when you're running this on a GPU, there will be specific kernels which are going to be used explicitly, like for if it's like a 2.4 format. And they will, instead of using like, I know, BF16 tensor cores, they will go to sparse tensor cores. And sparse tensor cores have like more flops than the normal ones.
All right. So like the hardware will detect based on the kernel which one to apply sparsity on, or which one to zero.
So yeah, it will not apply sparsity. It will just leverage the fact that your model is already sparse. If you have the 2.4, it will literally just subselect the unsparsified weights. So you'll have like a 2x smaller matrix. It will do the matrix multiplication of that, and then it will like unwrap the results back to where they are supposed to be. So it will just detect that it's 2.4, and it's going to run on sparse tensor cores.
Nice. So it said you call it 2.4. Is it named 2.4?
Yeah, it's 2.4.
Like the number.
Yeah, that's right. The general format is NM, like NM, okay. But like the only thing we have right now is like 2.4. Yeah.
To like the numbers, or like to
you
can you type it in the chat if you can, like just for
is it like 2:4?
2:4. Yeah, that's right.
Oh, okay. 2:4.
2:4, yeah.
Okay.
Which literally sounds like out of the 4 consecutive weights, 2 have to be 0. That's the format.
Okay, cool.
And there is also a way now to combine this with quantization. So you do 2.4 model, produce sparse model, then you quantize that model, and then you just compound the gains from both of these.
Wow. So that's 2 times faster plus, further fraction faster.
It's 2 times faster according to NVIDIA documentation, but in practice it's not.
Not
always that.
We'll wait for the customers.
We'll
wait for the callback.
There's always some trade-off. It's not always as
of course. Expectation vs reality. Definitely, man. Started my life. And distillation, that's a different concept. But if you can just, while you're at it, just give a few words to explain it, and if quantization is ever involved in it or not.
Yeah, it's basically a process of taking a larger model, which we call a teacher model, and a smaller model, which is called a student model. And then we fine-tune both of them. We fine-tune the smaller model by just trying to teach the smaller model how to produce the same outputs that the larger model produced. So you take input batch, you pass that through a larger model, you get some target outputs, and then you take the smaller model, you do the forward pass with the smaller model, and then you compare that and see, how similar my outputs are to the outputs of the larger model. If they are dissimilar, okay, let's optimize to be as similar as possible to the outputs of the larger model.
So that's like reinforcement learning.
Well, yeah, I guess you can look at it, except that you don't have all this like verifiers, feedback loops, and so on. I mean, one feedback loop is the loss that you're getting. It's just that in the standard setup, when you're fine-tuning, you're usually optimizing for cross entropy loss, right? So you have one like a golden label that you just want to predict. Whereas when you have a teacher, you actually get the full distribution on the outputs. And then you try to match that distribution of the teacher.
And it's up to you. Like when do you realize it's over? It's like at the end of the train, like the distillation. Is there a limit, or is it like it's up to your samples or inputs?
It's up to you. It's standard fine-tuning process. It's literally just the loss function that you're optimizing is slightly more complex now.
Nice.
That's the only difference.
Right. So it could be days, it could be hours. It's up to you.
Yeah, I mean, it's definitely more expensive because instead of just training one model, now you have to load the teacher, and you have to do forward pass through a teacher, which is usually a larger model. So you have to pay additional cost in terms of the runtime and GPU memory. Yeah,
got you. But once you're done, the distilled model is like super small compared to the original, right? So like you can have the DeepSeek Air 1 and just apply it anywhere eventually.
Yeah.
I mean, like distill it on the
if
Llama.
you have if you have resources to run the training with such large model. One special case where we saw the distillation being very useful is in producing the 2-4 sparse models. We have like the problem with, so the good thing about quantization is that you can do it in one shot. So you train a model, at the end you do like, you quantize, do this like post-training quantization. You do it, as Colin said, in a couple of minutes, you have like really good high quality model. Like, whereas with sparsity, this is not going to happen. If you do 2-4 in this like one shot regime, like the model is going to collapse completely. It's really hard because you're removing like 50% of the weights at each layer. So for sparsity, you always need to do a little bit of fine tuning. And where knowledge distillation really helps, for example, in this case, you take Llama model, 8B, you do 2-4 pruning, and then you fine tune it with unpruned, like the original Llama model, and then you distill the intermediate activations. So you train a smaller model, which is now 2-4 sparse, to follow the activations of the original unpruned model. And this gets you like a really, really good model. That's, for example, how we released a sparse Llama 3 8B model. We did literally pre-training by following this approach. Like we had some like distillation scheme where we would distill all of the intermediate activations from unpruned model.
So like you took a teacher model like a 405B or something?
You can take whatever you want. It's just a matter of the cost, whether you can run such large model during training, and how do you map activations of a larger model into activations of a smaller model, because usually they have different shapes, right? If you take the models of the same size, the intermediate shapes are all the same. If you take 405B, then you have to have some intermediate mapping from the large space of the larger model into smaller activation space of a smaller model.
Yeah, because the parameters are, it's
number of parameters is different. There's more layers, like 3 times more layers. Yeah, it's very easy when it's like 1-to-1. You just like map each layer to each layer. Whereas if it's larger, then you have to think a bit more about it.
Map it. All right. But there are people doing it. Like people are distilling. Like those who have the means. I mean.
Yes.
In the basement.
Of course. Yeah. I mean, it's like very, very. I think it's probably the only way right now to produce high quality sparse models. There is no other way to do it. Yeah.
Nice. So like back to the sort of extreme quantization. Now you just mentioned 𝐓𝐞𝐜. Was that 𝐓𝐞𝐜 T2 or something?
K2.
K2. Wow. Okay. Yeah. 𝐓𝐞𝐜. Like it reminds me of Kimi Antonelli, F1 driver. Anyway, so 𝐓𝐞𝐜 is currently available at a 2-bit quantization from 𝐿LM team, which is kind of crazy. Like you have fresh. What do you think if these like highly quantized models where they get to apparently like on sloth sometimes like gain 70% space gain or saving from like the original model, right? So like you have the UDI now, which is like a sort of quantized naming convention for unsloth quantization. They did that for DeepSeek v3 R1 with like 80% size reduction. Sometimes 271 bits, sometimes 166, 158. Again, like this is like dynamic, right? Dynamic quantizations. Like you're not even sure it's like 1 everywhere, 2 everywhere. It's not like a half. It's 66, 58, 71. It's like, what do you think? Is this the future, or is it maybe too soon or too aggressive, or there's like a maybe like a sweet spot between like those, especially because everybody wants to use DeepSeek today, right? So like we're using Llama 3, fine, but if you want to own your AI and you want to have like benchmark performance as good as closed models, you cannot actually compete with Llama 3. I mean, at least you cannot compete with 70B or something. Like you have to run something that is maybe more, like trained with more parameters, like a heavy lifter like DeepSeek. But in the meantime, it couldn't even fit in one GPU. It's many nodes sometimes for like 700 gigs. So maybe to call in first, what are your thoughts on it? Like, what's your take?
I think there's always going to be issue with going to like genuine 2-bit average, like without something like pruning, which would only effectively make it 2 bits. I don't think that there's like people run it at 2 bits for fun. Like, yeah, it makes good outputs, but I think overall it's not reliable. Like forever, people asked to put out like these tiny quantization, like 7B, like releasing the it's the IQ 1M that I put out of 70. I don't even do with the 1S because I think that it just gets way too small. There's not much you can do to save the actual. Like it'll generate and it'll have some good generations once in a while, but overall it's just going to be too damaged to actually produce meaningful output at scale. So like there is definitely like somewhere around 3 bits is definitely still completely viable. And I think is definitely worth running, especially as a consumer. I still wouldn't do it from an enterprise perspective. Like 4 is already kind of pushing the enterprise level of things. Like you really need that reliability. Like Eldar's nodding along, like he knows. Like yeah, AWQ is usable, but it definitely pushes the boundaries of what you should be using as a real deployment that is you need to rely on.
So, and Eldar, what's your take?
100% agree with everything that Colin just said. Basically, like, yeah, 3 and 4-bit, I think that's, at least right now, like that's the limit where you actually still get a decent model which has like maybe 1 to up to 5% maybe drop in accuracy or something like that. And it's pretty good for most applications. Yeah, below that, yeah, I think accuracy starts collapsing, especially in enterprise use cases where like usually customers are not willing to accept larger drops in accuracy because it kind of then becomes like a really garbage application. Yeah, like 3-4 bits seems to be the limit, at least right now.
To your point, DeepSeek was trained on an FP8, right? Do you think with the new hardware that we're having today with FP4 tensors, like those foundation model, the producer of those foundation model would just start the train on FP4?
The problem with that is that would you then need to go to 1400 billion parameters? Like DeepSeek is gigantic, and I guess I wonder, does its size, like it's probably not a 1-to-1 or like 1-to-2 ratio kind of thing, but if it was trained at BF16, could it theoretically have fit in closer to 400 billion parameters? I don't have an answer for that. I don't know if anyone has a solid answer for that, but definitely FP4, like the lower you go, the more parameters you're going to need just to have the information density that is required for models this intelligent.
What's the ratio, by the way? It's like the lower you go, the more parameters you have. Like, is there a rule of thumb, or like this is
I don't have
dark math? Eldar?
There are no rules here. The larger the model you can fit on your hardware, the better, I guess. At least for
but
huge
like
companies
like,
who are training them.
when you go, like when you decide, hey, let's say like I'm Mark Zuckerberg, I want to train my Llama 5 in FP4. Does that mean that like it won't be 405, but it would be like like a 1 gig 1 gig billion?
I think the way that this works, at least for these large companies, that they actually design the architectures for their specific needs. Like, for example, they have specific deployments in mind where they know they can fit this, and then they kind of go back and design an architecture of a model which specifically fits those needs. And yeah, this is kind of behind the closed door, so you can't actually tell what's behind it.
Well, but DeepSeek is sharing a bit sometimes, like they're more open with their process, no?
Yeah, definitely. Like you get more insights into that design process, and you can see that there's still like there's this kind of shift towards MOEs, right? So we are like taking these models, we are adding more and more experts, because now, at least in these deployments where we are deploying these very large models, we try to parallelize a lot across the experts. Like we do the expert parallelism to kind of like split them across the compute that we have.
Mm.
But then it becomes this kind of question of how many experts, how many layers, and so on. And I think this both usually depends on what hardware do you have and what do you have in mind for the target goal of the deployment.
Yeah. I think 𝐂𝐞𝐜𝐬 has 32 billion expert active out of
So
the
it's
trillion.
Yeah, it's the
Right?
number of parameters. Yeah, but the number of experts that they have is like 300 and something.
Yeah,
so they
384.
So it's like what,
Yeah.
64 active, 62 something. I think I've seen like around this 60-ish in one of the table, but
yeah, I'm not
anyway.
sure.
So
I'm not sure.
yeah. So like, it's still possible though. Like, they can come with a model trained on FP4. It may be gigantic in terms of parameter, but like it could exist in the future.
Of course. Yeah.
Right. And then those models could be quantized as well. And is it even possible to quantize an FP4?
It's going to already be in FP4. Yeah. So then the
Yeah.
question
So like,
is,
what's
do you want
the
to
point
push
of
more?
quantizing an FP4?
I mean, yeah, that's the question. Do you want to push for more, like below
Like
that,
2 bits?
or that's good enough? Yeah. I mean, if you want, you can do it. No one's going to stop you.
But like then it would be hell. It's like, I'm not a researcher, so like, don't take my word for it. But when you go from 4 to 2, it's not that a big of a change in terms of weight bits. The depth is not as different.
Yeah, but the problem is that when you train at FP4, you're probably making the weights excessively dense compared to if you're training at BF16, where there's a lot of extra noise going on. Like, you have to go for extreme density to make it worth it.
All right. So like, I don't know. Like, hopefully there will be a version where they have like a decent amount of parameters without killing everyone and having to store it in 20 nodes just because it's an FP4, right? And now with the future of LLMs, we have that on CPU, we have that on TPU, we have that on Gaudi, we have that on GPU, NVIDIA, AMD. We recently have Google releasing Google AI Edge, where they can run a Llama maybe 3N or Llama wherever, Llama 3 series, I'd say. GGUF version, it seems like, run on Android, on their app, the Google AI Edge. What's your take on it? Would it take a new type of hardware to run inference on mobile or on edge hardware, or we could just use the Snapdragon that we have in all our phones, and with smaller models that can fit like 1 billion? Especially there's a sort of a technique from Gemini lately where they have it's like a active, I wouldn't call it expert, but they have like a 1 billion parameter active, and then like the third 3 or 4, the 2 others are not active all the time, are not loaded. So it's not expert, but like it's their own architecture where you want to have everything loaded by default when you do the inference. So what do you guys think of like maybe the future version of inference on edge? Would it be trying to adapt to the current hardware, or we will come with like a new series of hardware that would be like specifically designed to run inference on them, and not something that used to be run for graphical rendering and crypto, and then also, since it's parallelizing operations, use it for inference? What do you guys think? I'm starting with Colin. Do you think it's are you seeing, do you expect this to happen where we'll see like a new generation of hardware, or like the model would just try to adapt to?
Well, we already have, to some effect, we have these NPUs that come in smartphones these days and in laptops and such. But I don't think they're particularly utilized, at least not from a like a language model perspective. They're used more for what people would actually call like AI algorithms, and like these days it's called AI, but before it would just be called a neural net. So I don't know if maybe those NPUs will evolve. We definitely have more of a focus on CPU and GPU at this time. ARM has some great optimizations. GPUs are obviously extremely good in general at running models, but it wouldn't surprise me if the NPUs kind of kept evolving and kept growing to cover a larger amount and maybe even start just running the large language models purely on the NPU. I think Apple's probably going to be the first one to do that because they've got the whole vertical integration going on. But Google designs their own, their G tensor. Maybe they'll have it with the G6 or something, and they'll start doing massive NPUs with full access to memory as well.
Interesting. Well, Apple is even in Mistral right now. They're into acquiring them, so that would be maybe a nice marriage. But look, that begs the question: if we have like a new generation of NPUs, would we have like dedicated models for mobiles eventually, or it would be like just one version and then?
There might be an idea of trying to have multiple different models that are like each good at a specific task and like loaded up on the fly. I think there was something from Apple about almost a LoRA sort of situation where they had one like main model and then adapters that specialized it at specific tasks. I don't know if that's strictly necessary. Like models are getting really, really smart these days, and with things like MCP, like tool usage becoming much more standardized and much more prevalent, I think having one smarter model with maybe some kind of adapter LoRA to push it in one direction or another, combined with tool use, is really what it's going to look like in the future.
Interesting. Eldar, any word?
Yeah, maybe just to add on top of that, like the Apple example is a really good one, but I think Character AI actually did a really large scale deployment of this specific use case where you have a ton of different LoRa adapters. So you have a backbone model, which is always there, but then you just do hot swapping of the LoRa adapters, which are fine tuned for specific, I think in their case, it's like different characters for their app. But yeah, you just kind of flip over the adapters based on the application.
So the adapters will it just be targeting a specific task or a specific hardware?
Yeah, I don't know the details, but for example, like in the Character AI, like you can have a LoRa adapter which represents, I know, Cristiano Ronaldo. The other adapter represents like Lionel Messi, and the third one represents some other like celebrity. And then based on the user that you're interacting with, you're just like loading the different adapters, while your backbone model is always there. So you don't need to spend the time to load the larger one. Yeah.
Oh, interesting. That's cool. Okay, now we have quantization, but we need to, make sure that the quantization is not garbage. Like the quality, like the accuracy, right? And this is why we also have evaluation, evals for quantization. So we have something called perplexity, KL divergence, KDL. I wouldn't name it completely because I'd completely be mistaken for sure. MMLU. And I wanted to ask Colin to talk about perplexity and also like why KDL. What is KDL and why is it better in most of the cases? I think you explained that to me online in Twitter once, but I would like the audience to listen to you.
Yeah, so perplexity is this idea that given a series of text, how surprised is the model by the next word? And so assuming a very high quality corpus of text, low perplexity is what you're most hoping for. You want it to be very low. You want the model to not be surprised by what the next word is, because ideally it should be quite smart and able to predict within reasonable human text. What KLD or KL divergence comes in and does is it kind of tries to compare two models and the difference in their level of surprise. So if you quantize, especially if you quantize in a way that targets a specific data set, and then you were to then measure perplexity against that data set, that quantized model is likely to not be at all surprised by the text that's in there because it's been specifically optimized to more likely guess that text. And And so that's why, like, if you just look at the perplexity number, it's kind of a good smoke test. If a very high number shows up, you know something is probably wrong. Something's going off here. Like 10 or higher is like, whoa, what's going on? But if you get, 2 to 5, you're like, okay, this is probably competent. Everything's probably okay. Especially when it comes to quantization, like those numbers can really balloon rapidly. But if you have an original model with a specific perplexity and a quantized version of that model with another specific perplexity, comparing them only gives like part of the story. It says like, okay, yeah, it's still like you didn't destroy it. It's still pretty good at guessing this text, all things considered. What KLD comes in and does is it actually does a more specific measurement of the tokens that are being predicted and how likely it is at any step, like what's the 99th percentile of tokens that it guesses wrong. How often is the top token that it predicts the exact same token? Things like that. Like how likely is it to be very different in its prediction? So those kinds of measurements kind of paint a more full picture. Theoretically speaking, assuming that data is not being contaminated in any way, they are extremely correlated, perplexity and KLD. And so like in a vacuum, one should mostly give you the answer to the other. But when you really want to get into the specifics and you really want to push for accurate measurement, getting that KLD, especially on a relatively random set of data that the models for sure didn't see during the quantization process, is really important for painting that more full picture and letting you know exactly how similar the models are after quantization.
So basically, perplexity, you compare the result from like a full precision model based on an input output to the quantized one, right? And then perplexity is like, hey, it's like talking about ice cream, and then it's talking about a trunk of a car, no relation.
Yeah.
So that's like high perplexity because, hey, you're perplexed when you hear something like a story that, like a punchline that has nothing to do with the beginning of the story, something like that, right? And KDL is more comparing like the probability of those perplexity or like those bad precision, like bad like inaccuracy probability.
Yeah, and importantly, like it's entirely possible that both the original model and the quantized model are really bad at predicting this text for some reason. But the important thing is, are they similarly bad? Like, are they behaving in the same way? Or are they similarly good? Are they usually trying to predict the same token, but like it doesn't matter if it's wrong? Are they still doing the same thing? And that's where it's important.
Interesting. So like in Google, in GitHub, people can just maybe check KLD now, maybe a bit more than perplexity is like as much or even more from now on.
Yeah, unfortunately, it is much more expensive to do because you have to run it against the original model and like save that, and then run it against the quantized model and save that. And so it is a more time-consuming process and a more compute-intensive process than just measuring the perplexity, which again is usually enough for most people because it just gives you that little quick smoke test of okay, is it completely off the rails, or are we looking at like did everything kind of go okay? And that's usually all people really care about, except for when you get into the real nitty gritty.
Yeah, that's why Q4K is like everybody's best model in terms of perplexity, because it's a win-win for everything. But like are you seeing a pattern of quantizer using KLD as a sort of a benchmark of quality of their quantized model, or it's up to who quantizes?
It's kind of up to who. I know that like Unsloth has released a few here and there, mostly when the original DeepSeek v3 came out, because there was some deficiencies in the way that Llama.cpp was quantizing particularly large MOE models. We hadn't seen them in a while, so no one was really doing anything to try to optimize for them. And so there was a couple of key areas that needed some updating. And with those updates, it did massively improve the perplexity and the KLD. But overall, no, most people like don't bother. It's a bit of a excessive metric. I like it. It's a lot of useful information. And if you really like are trying to especially optimize something for some reason, like, or you're trying to find a new quantization format, like that makes more sense in terms of what layer get quantized to what level, like it's super helpful for that. But overall, it's not like you don't really need it. You'll usually do pretty okay with just perplexity. And if you really wanted to, you could run some benchmarks. But yeah, KLD is definitely what I would call the gold standard of finding out the quality of the quantization in relation to the original model. It doesn't tell you that it's a good model. It just tells you that it's similar to the original.
How similar?
Yeah, exactly.
Nice. Gotcha. Glad. Nice to know that you're a perfectionist. So you're keeping up with the KLDs and stuff. That's a good habit to have. Eldar, on the vLLM side, like LLM compressor, once you're done, like you applied your recipe, how do your evals for your quantized model?
It's very similar story, actually. So maybe just to mention one thing regarding the KL divergence. This is actually what is exactly used in the knowledge distillation. So what we talked before, when you have larger teacher and smaller like a student model, KL divergence is the metric you actually want to optimize for. Because for each token at the output, it tells you how similar is the probability distribution that one model produced versus the other. And in the case of quantization now, just the teacher is unquantized model and the student is a smaller quantized one. Yeah, and it's like a perfect metric kind of just to get like this, like a similarity score against the larger or unquantized model. However, one main kind of problem, at least on the kind of like when you're trying to present the results, it's not that clear on what does it mean when you drop 0.5 in KL divergence or perplexity. That's why, at least internally, we do use perplexity and KL divergence for our own investigation. But kind of when we want to release a model, then we kind of switch over a bit to like these more standardized tests like MMLU, GSM8K, human eval, I don't know, arena hard, and so on. So it's something where you actually have accuracy. So you can tell to a user, okay, if you take unquantized model, the accuracy is, I don't know, 85. If you take the quantized one, accuracy is 84. So it's kind of what we got used to, like, scale 0 to 100, and I can exactly see how bad my model is relative to the
right. So like you compared it like it was a completely different model in a benchmark. So because back in the days, like I was using GGUFs and I was comparing perplexity, and I was like, okay, this value is fine, and I will try it again and then like see the vibe, how it looks like, how it it replies to me. Are the output good, or is it like completely hallucinated from like the first prompt? Right. And then I would see the MMLU. I would see, how do you call it? GPQA? Is that it?
Yeah.
Yes. GPQA, or like the math. And like now we have the SWE benchmarks and stuff. So internally, you would go for perplexity and KLD, but like with the customers, they have only one language, which is like the LM Arena benchmarks, right? But like for you as a technician, as like a scientist, which one would you go for?
So when you're quantizing a model, usually what you're doing, you have to play a bit with hyperparameters, right? Like the size of the calibration data, some like different dampening factors, blah, blah, blah. And during this process, you want something that you can compute very quickly. Because you're going to run, like this is like iterative process, you're optimizing for something. So you're going to produce a lot of quantized models. So you want something that you can compute very quickly just to judge the quality of one versus the other. And in this case, like perplexity, for example, is like a very good, or KL divergence is very good. You can run it very quickly. You get the feedback immediately, and you see, okay, this is a better model on this one, I'm going to ship this one. And the ones you're ready in this kind of exploration phase, then you start running these like a little bit more expensive benchmarks like MMLU, Arena Hard, and so on. And that's basically what you all like present to the outside world, right? This is because that's what people usually care about. If I take a quantized model, what's the drop on the math 500 that I'm going to see?
Yeah, so
like
that's
1% or 20%. Yeah.
You showing your watch on the street and say like, this is like a pretty much like a real Rolex, but it's cheaper.
Okay. Yeah, because it's very hard to like at least for like non-technical people, it's very hard to like quantify whether a drop in perplexity of, if perplexity dropped from 7 to 5, what does that mean? Is the model like completely destroyed, or it's still like good enough?
You still gotta try it.
Yeah, that's right. You have to try it. But here, if you say, accuracy drop from 85 to 83, it's something I can live with, right?
Yeah. Candid question though, like, do you guys believe in those benchmarks? Because some models are really trained based on these benchmarks. So,
not really.
Right?
Not really.
It's like, is it like all hype shit?
There is a
marketing
ton there is a ton of papers which actually show that a lot of these models are kind of contaminated with the benchmarks. Like, I'm not sure if you have. Yeah, I mean, like.
Do you think Llama 4 has been a bit? Because a lot of people accused them at some point.
I don't know. I mean, so there's this process of they're probably not doing that intentionally. That's like the first thing to clear up.
That's what I heard everywhere.
But the problem is that the pre-trained data is like, 15 trillions of tokens, right? So it's very hard kind of to say reliably that there are no examples of MMLU, for example, samples in those 15 trillion tokens. And there's specifically, I think, paper from maybe a year or two ago, which showed that if you take MMLU benchmark, which is like a multiple choice. So you have a question, you have 4 answers, A, B, C, D. And then you evaluate the model, you get 1 score. And then if you just flip the order, of the answers, instead of doing A, B, C, D, you just flip maybe A and C. Like all of the state-of-the-art models dropped by 5 to 20 points in accuracy. If you just flip, so everything is the same question, the same answer, you just flip them, and the accuracy drop, which is probably if you're taking 15 trillion tokens from internet, there is a high chance that you will probably pick up unintentionally some form of the evil benchmarks in there, and the model is gonna say it.
Yeah, so to be taken by a big grain of salt.
Yeah, yeah. That's why we usually prefer, at least when working with customers, like these general benchmarks are a good kind of first step. Just to get the gist of whether the model is producing garbage or not. But then usually they have some specific applications where they're using LLMs. Whether you're generating some specific code for some specific language, whether you're doing summarizing the text, blah, blah, and then you actually evaluate in that setup, because that's what matters in the end, right? If you're deploying a model for summarization of some specific set of documents, you actually want to evaluate it there. And that's what we use as the final kind of score and metric on how good quantization is relative to the baseline.
Interesting.
And 𝐂�Me, by the way, they're saying that it's it's made for agentic AI. It's really trained for agentic use. Do you actually believe in this kind of premises and this kind of claim because call tooling was there a long time ago? I mean, Llama had function calling, we're there. And a lot of what we're seeing today in LangGraph is using the existing models, right? So it's not like you need to create a new one that is you can't say oh, this is specific to agents. While all the agents that are running until now were using other models. How credible would be this kind of claims? Obviously, it's been a couple of days since it was released, but did you believe there's a agentic only model?
I mean, not necessarily agentic only, but agentic focus does not surprise me. Yeah. There is definitely optimizations to be made with, function calling, things like that, dealing with the results of it, treating them as ground truths, where, models of old, they could run functions. They could figure it out. They were smart enough to understand formatting of JSON, things like that. But adding it to the training data and focusing specifically on it is obviously quite important and helpful for stability of using these tools and becoming an agentic platform.
Interesting. Eldar, any thoughts?
I mean, I 100% agree with what Colin said. Basically, it's just that they are leaning a little bit more towards being able to know and to leverage the tools and function calls when they need them. Because previously, for example, Llama and all these models, it's just a bunch of text. You just train it on that, and it's doing next token prediction. Whatever is the most likely next token, it's going to predict it. Whereas here, you actually, the model knows that it can use these tools when they're needed. Yeah.
So would you say wait and see then until people like, you know, get some feedback out of a model like this?
Yeah, I'm sure it'll be good, and I'm sure it'll be good at some things. I don't know if it'll be like necessarily state of the art, like the level that people are gonna have to quantize it to run it locally. It's only gonna be for fun, like just to say like, hey, I ran a 1 trillion parameter model, and that is cool. That is very cool. Yeah. Don't get me wrong, but like DeepSeek, even the original one, it's difficult to run it quickly as well. Like the sheer size that it requires makes the infrastructure quite difficult to maintain. So it has been revolutionary for like the open source world. They released and like it's nice that they released so much interesting stuff with it, like all their learnings. They've got their MLA cache, which was really impressive. A lot of stuff that they did was super cool. And kudos to them for releasing it all openly. But in terms of running it local and being like a local model, it is difficult to say that it is going to change up a lot of stuff, at least for people. Most of the workflows that I know of.
You bet, you bet. Well, you know, they can always run it on Grok.
Exactly.
Or some inference service, for sure. So now let's talk about Hugging Face. Like we're trying to bring this puppy home. So what can you say about the role of Hugging Face? I know there was something before Hugging Face before, but like all over the journey, how was it helpful for you guys or for the community or maybe in quantization specifically? What do you have to say about the role of Hugging Face in the past, currently, and in the future too, regarding that? Colin?
I mean, Hugging Face is like a revolution on especially open source. Like the fact that they allow me to store, you can pull up my HF storage file if you want to show that real quick. Like the fact that they allow me to store, I think it's up to like half a petabyte.
Half a petabyte. That's you got to pay a premium for it, or
no?
Free.
No. Yeah, because so they have a private allocation that's free, and then you have to pay if you want more private storage. But if you publish, which is what I do with everything, because why wouldn't I? They allow you to upload. Well, I mean, I'm sure there's restrictions in terms of like abuse potential, but they allow you to upload as much as you want, which is just awesome. And so that's been like, that's the only reason that I have this hobby, is because they allow me to host it somewhere. But then they also, they take it a step further because they have, safe tensors, they have transformers, like they also contribute to the running of these models, not just the storage. So they're really coming from both ends of it, and it's absolutely fantastic what they do. I have tons of respect for the company. I love that they're profitable. Like they said that they don't even need to be, but they are. So that's awesome.
Well, who do you think pays for the hardware?
Well, they've got there's a lot of enterprise use enterprise accounts with Hugging Face. So they make money off of that. They make money off of Inference. They've like some of the spaces you pay for those GPUs. Like you can get spaces for free, but you can pay also for GPUs. So like a lot of the most popular spaces will probably be backed by a paid GPU. So things like that. And then obviously they have tons of sponsors as well. But yeah, like they're doing some great stuff for the community. Like absolutely unreal, unbelievable to expect them to do it. And the fact that they continue to and do it profitably is fantastic.
That's insane. This is like a Wikipedia of LLMs or AI.
Except with like orders of magnitude more storage costs.
Exactly. Yes, because articles aren't that heavy.
Yeah,
for sure. Eldar, any additional thought?
Yeah, I mean, like I think the case when like Hugging Face goes down and then you open up Twitter and Reddit, it's like AGI slowed down by 1 hour or whatever, because like I mean that's like a clear indicator of how important they are to the entire community.
Wow.
Yeah, and all of the standards that they set in place like became like a de facto standards in industry, which also made our life like 10 times easier, because now we just kind of like hook on top of that and build on top of that. For example, like with compressed answers, it's basically just extension of saved answers. So they built the format. They said, oh, this is how you save the model. And now we just kind of say, okay, if it's a quantize, you just save it like this, but it's still like saved answers. It's everything there. Also, like with the config.json, tokenizer, and so on, we just like build on top of that. If it's a quantized model, we just in config.json, we add one field, quantization config, and specify that. And everything else is kind of standard, works across all of the libraries. It's like I don't know, like I think like the most important piece of the open source work right now. Yeah,
that's sick. And how many people do you think work for them? I think there are many, or is this just like a startup sized company?
I think it's closer to startup sized.
Really?
Probably. Yeah.
Interesting.
Their Wikipedia claims 250 employees, which is not small by any stretch, but it's definitely closer to startup size.
Okay, yeah, because in terms of size, in terms of like loads, they really have to take care of a lot of things. Like just guarantee and availability.
Yeah.
That's the benefit. That's the benefit of open source, right? Because they're working in open. They also actually, they set the standard. They like provided the platform for people to work with, kind of like collaborative manner, and now they're kind of benefiting a lot from that because now everyone wants to integrate into transformers. I see this across many research papers. Whenever people invent a new technique, like the main target is I want to go to transformers to contribute my code there, and they kind of get it for free now because they set the standard, they did the hard work, and now they're benefiting from that. Yeah,
that's sick. Kudos to them because it's working. I may think even maybe cloud providers would give them some free hardware or free hosting just because it's an open source kind of workload. Maybe they have behind the scenes some sort of partnership with providers because
almost
I don't
certainly
think it's done at home. Yeah.
And like they also they still have the startup vibe. Like so when Zet storage was being rolled out, they were in contact with me directly. And I was like in contact with key developers. Like if I ran into an issue, I pinged them and they were working on it like within a half an hour, like trying to get me back on block because this was this new system. It's hugely important for their storage costs moving forward.
Of course.
And they wanted to be as smooth as possible and make sure that like I had a smooth experience. So that was just awesome with them. Nice. They also they hired the NGXen over on Llama.cpp. You might have seen him. He's
the guy. He had like that thing with like a video lately. He made like a camera and they using the model. It was detecting whatever it was doing and stuff like that.
So he's been dragging Llama.cpp kicking and screaming towards multimodality and has been doing exceptional work. But he is employed by Hugging Face to work on Llama.cpp, which is crazy to think about also because that's like in one way it's a competing platform. Because they have transformers and now this is GGUF, but then in another way, like they have such a huge amount of support for GGUF. Like they have the native viewing of files on Hugging Face platform. Like they are extremely supportive of other platforms, and I think that's awesome from that as well.
Yeah, we may have at some point like equal number of GGUF models in Hugging Face.
Yeah,
like if it continues this way, right? It will, I'm not saying it's the case right now, but like it's really promising.
It is.
Yeah. No, I know that guy. And Ksat, just for the audience that don't know, can you just tell like a couple of words what it means? Like it's just, and I know it's in terms of loading the files and sort of a sparsity somehow.
Sorry, which part are you talking about?
The 𝐓𝐞𝐡 storage.
Oh, right. Sorry. Yes. So basically, it was a big focus on trying to deduplicate data. So a lot of, in particular, GGUF models, but probably all formats in general. But they add a lot of layers. Like you'll put that to Q4 for Q4KM. Then Q4KS will also have most of the layers at Q4, and then Q5 will also have some layers at Q4, and then Q4KM will have some at Q6, and Q6 also has. So the point is like a lot of those layers are completely identical across multiple.
Redundant.
Completely redundant, at least from a storage perspective. So Zet introduced this deduplication that allows it. So basically, if you go to upload a file, it'll locally first break it up into chunks and hash them, compare it to what Hugging Face has stored, and see if it can reuse some of its like. So it says, okay, no, you don't have to send that to us. We've already got it. Send us the rest. And then, so it speeds up uploads. It lowers their storage costs. It's awesome. Like, great technology that they've implemented and very beneficial both for end users and enterprise alike.
That's cool. That's cool. So does it have to be the same name, or how
No,
does
everything.
it get?
No. It chunks the files up and hashes it. So at its base level, it does not matter what you're uploading. If
So like, let's say I have Llama Q4K, and then I have Llama, like the same type of Llama, but like maybe a different quantization, or maybe
like
same quantization version, but like a different name. Like a guy would just call it maybe the block Llama, but it's the same model. More or less the same quantization. It's just like one is S, one is M, but the naming of the GGUF file is completely out of track.
No,
would it guess?
It would figure it out, because it's at a data level that it's not doing any kind of like string comparisons, block level data comparisons, to figure out whether it's stored or not already. It's very cool.
That's super cool. All right, there's also something we have like a huge community in Reddit. It's called Localllama. I think Eldar heard about it too. That's where everybody's gathering in order to rant or share like some new stuff that they run, mostly local, of course. And apparently recently something happened. Maybe the moderator, I don't know, like he may took an indefinite vacation, or he just got tired to moderate the Reddit group. Colin, did you have any feedback or any like update on the stick? Because apparently everything was frozen. Is that what happened?
It was a little wild for a bit there. There is now a moderator in place, but for a period of time, whoever was moderating it at the time just turned on the auto moderator bot to delete everything, removed themselves as a moderator, and deleted their account. So I don't really know what happened to him or why he decided to do it in such a violent way. Someone must have pissed him off. But luckily, they opened up a petition to the Reddit admins. Reddit admins came in and it appointed a new moderator. So it is back open. Everything's fine now. We're getting our submissions again. But there was a couple of days where it's like, I don't know where to get my news.
Wow. Yeah, of course. They have 75K members so far. And what I noticed is
500,000. Are you on local LLM?
Local LLM, yeah.
Yeah, Localllama is the bigger one.
Oh, Localllama. Oh, right.
Yeah, they just hit 500,000 today.
500,000.
Yeah.
Jesus. Localllama. Yes, and the thing is, during there was like Zuckerberg organized something like a keynote called I don't know. It was like a small conference where he brought the Databricks CEO at some point, and they were talking about like the size of the models to be used, the 405B, and then the CEO of Databricks said, like, most of the time, like we were surprised our customers were like using the 7B, and they're like, they don't care as long as it does like the basic task that it was asked. And he made a shout out to Localllama, by the way. So like that's how that's how famous it is. That's so cool. Eldar, is there like an equivalent, because this is Localllama, but like, is there an equivalent in Reddit for vLLM fans? I know they have a Slack for sure, but like, is there like a Discord?
I'm using the Localllama as well, so
okay, cool.
It's expanded beyond Llama.
All right,
yeah,
cool.
I mean, there is like a vLLM Slack where people like share their problems, ask questions, and a lot of the vLLM developers are actually there. So that's like for like a technical discussions, just exclusively about vLLM. But yeah, for anything else out of that, Localllama.
Yeah. So the Slack is for PhD students. All right. And now just to wrap it up, actually, it was like very, very informative. I really loved it, and I hope like people will have the chance to rewatch it again. I would do it as well. I will share LinkedIn. Apparently, LinkedIn stream didn't work, and I'm so sorry for everyone.
I think it did.
It did?
Yeah.
I know some people
I
complained.
was watching it earlier.
So, really?
To see if that was
Okay,
on,
cool.
yeah.
Cool, good to know, because somebody said, it's not working on LinkedIn, and I was like, damn, I don't have time to deal with this.
No, it's
right
up,
now.
and Stephen earlier in the chat was from LinkedIn, so definitely. It
Oh,
was working.
cool. That's super nice.
It was probably just delayed.
Great. I'm so happy. I'm super glad. And just to wrap it up, I just want to like some word of wisdom, hopefulness, wishfulness, maybe from you guys about the future of not just quantization, but how the consumption of LLM would be in the future. Like, what do you envision or hope for beyond the crappy hype that we've been seeing? People putting AI expert in their LinkedIn profile while they have no clue what AI is. Somebody else put in a meme saying the only expert in AI is AI, by the way, which is not bad. And yeah. So like, what would you think? What are your hopes actually? Because I don't care about the hype, but there is still a path, a future where everybody has maybe a contribution to do. Maybe some people that are not involved now will be involved tomorrow. You never know. Work will change, positions, roles also will be changing. Some people are saying, hey, you know what, this is like doomsday. AI will replace everything, and we will just lose our money, and then we'll ask for universal salary compensation because of that. But candidly, what do you guys are just picturing for the future and hoping eventually? Colin?
I mean, I am personally pretty hopeful. I know that there's a lot of doomsday scenarios that exist, and I understand that a lot of them are very possible. But I try to be hopeful just because I think that's where our path is. Especially when it comes from an open source world, like that gives me even more hope. I love a bunch of closed models. I use Claude Code extensively. It's amazing tool. And that tool also kind of gives me hope, like seeing myself be augmented by an AI tool is really cool. But the continuation of open source AIs, and I think we're going to see a trend of more and more companies releasing open source AIs, because we had, initially it was just really Meta releasing Llama, and then there were some Google models. Mistral was a model as well, but like there was only a few of them. Whereas nowadays, like it's becoming easier and easier for companies to create their own bespoke models, not just fine tunes. Like for example, our company RC is releasing their own foundational model. Like it's a brand new, not just a fine tune, and I think that's going to become more and more prevalent.
Congratulations, by the way.
Thanks. Well, open weight soon, hopefully. We're just putting the finishing touches. It's just not quite ready, but I'm super excited for that to come out. Cool. But like, I think that's going to be a trend going forward as well, is that we're going to see these companies have the ability to put out their own foundation models that are going to revolutionize specific areas of our lives, and I'm all about it and looking forward to it.
Interesting. Thanks for being honest. Eldar, your thoughts about the future of LLMs and AI in general?
Yeah, I mean, I do share that more or less similar opinions with Colin, because I still, it's very hard to imagine like there's like a very bad scenario with AI, given that we know how it works, we know what the the internals are of the LLMs. I think it's just like a productivity booster for all of us if we learn how to use it properly. And at least that's how I'm looking at it. Like kick off something that I don't want to do, go grab a dinner, come back, it's done. Move on with the task. It's like, I don't know, perfect thing, perfect like companion to have. Like it's very hard for me to imagine like anything kind of super bad coming out of it. Yeah, and on the other hand, like the push for open source is like I think that's, at least that's what we all believe in. all of these companies. I think even like Mark had like a really good podcast. I think it's like a Dvarkev podcast where he actually said like, we create the model, we pay the cost to like do the fine tuning, post trading, blah blah blah, all these things. Then we release the model, and then if community like improves it just a little bit more, we get a lot of like return on that investment. It was not like a waste of money. The fact that we trained the model, we gave it for free, because if anyone makes any kind of contributions, we also benefit from that. And we are seeing that in vLLM, in Llama.cpp, in transformers. Like it's very hard to keep up like with at least the state of AI these days if you're a company with 100, 200 people. But if you're like in open source, like you have like hundreds of like developers around the world, I think it's very easy to move forward and to much higher rate.
Amen to this. Amen to that, man. On my side, I've seen those memes. There's I think you've seen it where like the farmer was just telling the horse, hey, you're not going to be replaced by a tractor, but by another horse that would know how to use a tractor.
Yes.
So they've been some of these memes that actually confuse everyone about the future, and also what I don't like now is how everybody's taking advantage of the hype and selling like maybe misleading promises. And I think during the internet bubble, if you remember, back then they used to have positions like chief internet officer or internet president in companies, right? So like in 99, you used to have like CEOs and also CIOs, which is chief internet officer, right? And that's more or less what's going on right now, where you see like I actually didn't want to put any AI until like maybe 2 days ago or something in my profile, because like they used it so much, it's lost its meaning. You know what I mean? So you're seeing like chief AI officer, you're seeing AI leader, AI transformer or AI expert, while like they never read a paper in their life, right? Just because maybe they run a model, or they install like they run a model through Grok, maybe that makes them like an AI expert, or they watched a couple of videos, about DeepSeek. And I hope like in the future we'll have less of that fluff, where like AI everywhere, that like sauce that's put in every plate, every dish, and we'd have experts come forward without having to bring that that sign, that big sign on top, like, hey, I'm that chief or president or like magician, AI magician and stuff like that. Would just keep back. Like, I hope it will become boring. That's what I meant. Like in fewer words, I hope AI in the future will become so boring nobody's gonna, be tempted to put that in a profile or just brag about it. If that makes sense.
Nature's gonna deal with that, like over time, like all these things kind of settle down, and
it's gonna dilute.
You converge to a local minimum, and then you're fine. Yeah.
We'll have some distillation on that site.
Yeah.
All right. I really love this one. I actually wrote the blog. I read a lot of documentation, and I thought, people need to read about quantization, but they also need to listen and have people, experts like you, like amazing guests to talk about it. And I know it's like 2 hours and a half and more, but this is, like for the posterity, because people will get back to that video again, and you won't have to explain that thing another time, which is super cool, right? So like every time I run an AI a meetup here in Toronto, next week I'll be speaking, I will redirect them to this video, because I won't have to speak about quantization at all, because that's 2 hours worth of quantization content, and I'm so happy we've done that. We'll try to promote that as well. Again, my name is Kosseila, aka Cloud Dude. I'm the founder of Cloud Thrill. You'll see my blogs about vLLM in the future, and I also have a TechBeats Unplugged podcast. I had people like a bunch of people from the tech industries. I was thinking of guy from Kubernetes Hightower, sorry. And then yeah, so we'll be doing something else. We'll just giving our self permission to maybe suck, make mistakes, just learn in public. This is all I want today. We may have something else in the future, like another live stream. This is my first time ever, and hopefully it was interesting for everyone. And I really loved it, to be honest, and I can't wait to do that again with other guests. I hope it's not going to be the first time. Just apologies if we made any mistake. This is live, by the way, but I think it's been fairly decent so far. We didn't run that much. And I would like to thank Eldar Intro and Bartowski, aka 𝐓𝐞𝐡, and see you next time on TechBeats Live. Thanks, everyone. Thanks, Eldar. Thanks, Colin.
Good
See you
chatting.
next time. Appreciate it. Thank you so much,
Thank you,
everyone.
folks.
Cheers.
See ya. Have a nice
Cheers.
day.
Bye.